Multivariable calculus is just calculus but with more than one variable. For single variable calculus, we performed our operations on functions that looked like y equals f of x, where the function had one input value that generated one output value. We are going to be looking at functions that have more than one input variable. Here's the formal definition. Definition: a function f of two independent variables is a rule that assigns to each ordered pair xy in some set D exactly one real number, f of xy. There's no reason that we have to stop at just two input variables. We could have three or more independent variables and everything would still work the same. It's just that these are much more difficult to visualize, and so we'll primarily be sticking with two variables. And although we won't discuss it now, you may also want to think about what happens if you have multiple output variables. Just as with single variable functions, we have the concept of the domain of a function. Definition: the domain of a function f is the set of all inputs at which the function is defined. We are going to be using the so-called natural domain of the functions. What this means is that if the function is given as a formula, then unless explicitly told otherwise, the domain is the set of all points for which the function makes sense. The key things to look for are that values under a square root are non-negative, and that the denominators of fractions are not zero. For example, let's determine the domain of the function f of xy equals 1 over x minus y. We want to know the values of x and y that we can plug in and get a meaningful result. We can observe that the fraction makes sense as long as the denominator is not 0. In other words, we need x minus y to be not equal to 0, or y is not equal to x. We are going to draw this domain on the xy plane. We want everything except for the points that lie on the line y equals x. So we will shade in the whole plane except for a dashed line corresponding to the line y equals x. The dashed line is how we indicate that this collection of values is to be removed. This notation is also common when drawing the edge of other boundaries that are excluded, such as circles or rectangles. A slightly more complex example is f of xy equals the square root of 2x minus y plus 1. Here, we need the expression under the square root to be non-negative, so that 2x minus y plus 1 is greater than or equal to 0. In other words, y is less than or equal to 2x plus 1. The graph of that domain looks like this. Notice that we are using a solid line because we want the boundary to be included this time. The important thing here is that you're not trying to memorize any formulas. At this point in your mathematical career, you should be able to recognize when these types of expressions do and do not make sense by just thinking about it. The two big clues to look for are square roots and fractions. You should not take the square root of a negative number, and you should not divide by 0. As with single variable functions, there are multiple ways to represent functions of two variables. One of the first ways we learn to represent a function is by creating a chart of values. But rather than arranging the chart in a single column, it's usually better to make a two-dimensional table when working with a function of two variables. It's important to label the input values so you know which one is which. For reasons that will make sense shortly, the x values are in the vertical direction and they increase going down the page. We can then fill in every position with the number we get from the formula when we plug in the corresponding values. Another way to represent a function is with a graph. There are two input variables and one output variable, so we need to work in 3 dimensions. We will imagine that we've drawn the standard xy axis on a sheet of paper placed on a table with the positive x-axis pointing towards us. Notice that the y-axis would point to the right. We've drawn the xy grid in this picture for emphasis, and you should imagine looking down on the sheet of paper from above and rotating your head a little to get the normal orientation. Then the output function will be the height relative to the table, with positive numbers being above the table and negative numbers below. We will label this with the z-axis. Here is a graph of the function. Some people describe this as kind of like an upside-down bowl. Technically, this is known as a paraboloid. In math, we often call the graph a surface, and you should think of it like the outer surface of a ball or a vase. The surface itself is two-dimensional, meaning that a small piece of the surface looks like a plane, but the whole surface curves its way around in 3 dimensions. There's much more we can say about the geometry, but we'll leave that aside for now and focus on building up some more concepts. An important new element of 3-dimensional geometry is that we have 2 different orientations. In chemistry, this is known as chirality. The idea is that the mirror image of something in 3 dimensions is different from the original. If you've ever used work gloves and put a glove on the wrong hand, you've experienced this phenomenon. The same thing happens with our coordinate axes. There's a right-handed system and a left-handed system. In order for our images to be consistent, it's helpful to stick with the same system. Neither one is inherently better than the other, but the right-handed system is a more natural generalization for us. It's also how we set things up earlier. There are a number of ways to think about this. If you draw the x and y axes in the traditional way and lay the paper down on a table, the z-axis will point up out of the table towards your face. Another way that this is described is that if you point your index finger on your right hand in the positive x direction and your middle finger in the positive y direction, then raising your thumb points in the positive z direction. And yet another way to think about this is that if you think about grabbing the z-axis with your thumb pointing in the positive direction, the direction your fingers curl shows the rotation from the positive x-axis to the positive y-axis. Some students find it helpful to cut off the corner of a box and label the edges to get a physical manipulative to help develop the correct intuition. It will take some time and experience to determine which visualization works best for you. A good exercise is to draw your axes in a random orientation, being sure to note the positive direction, and then randomly label them as either x, y, or z. From this, are you able to determine which direction the remaining positive axis points? Here are a couple examples. Pause the video and give it a try. You should be able to get it with a little bit of thoughtful effort. In the next video, we'll begin to explore some common surfaces and some important formulas. In the xy plane, the lines x equal a and y equals b are not only basic, but fundamental to the coordinate system. When we put a bunch of these lines together, they give us our coordinate grid. Notice that the x equals 2 line is a vertical line that corresponds to all the points where the x coordinate is 2, and the y equals 3 line is a horizontal line that corresponds to all the points where the y coordinate is 3. These two lines form a rectangle with the axes, and the point 2, 3 is the corner of that rectangle. Another way to say this is that the point 2, 3 is the point that lies on the intersection of these two lines. We're going to take the same idea and apply it to 3 dimensions. Here is our right-handed coordinate grid. The point 2, 3, 1 can be found by moving 2 in the x direction, 3 in the y direction, and 1 in the z direction. Notice that the first two parts match up with what you normally do on the xy plane, and then we've added on the third movement in the third dimension. We're creating a 3-dimensional picture in a 2-dimensional medium, so we're going to help ourselves visualize a bit by turning this picture into a picture of a box. Notice that if we take away all the reference lines, it's impossible to visualize where on the grid the point is located. Again, these are the challenges of drawing 3-dimensional objects in 2 dimensions, so we'll put the box back. From this picture, we can identify the x equals 2 plane as being the plane that contains the front of the box. All the points in that plane have the property that their x-coordinate is 2. Notice that this is parallel to the yz plane, which is the plane formed by the y and z axes. We can similarly see that the y equals 3 plane is on the right side of the box parallel to the xz plane, and that the z equals 1 plane is the top of the box, which is parallel to the xy plane. The box we drew here is analogous to the rectangle we drew before in that the intersection of all 3 of these planes gives us the point 2, 3, 1. It's an important fact that all the sides of the box are perpendicular to each other. This is helpful because that means we can use the Pythagorean theorem to derive the distance formula in 3 dimensions. Remember that the Pythagorean theorem says that if you have a right triangle, then the sum of the squares of the legs is equal to the square of the hypotenuse. If we have a box where one corner is located at x0, y0, z0, and the opposite corner is located at x1, y1, z1, then we can use the Pythagorean theorem twice to get the length of the long diagonal. We first apply it once to get the length of the diagonal across one of the faces of the box, and then use that length in another right triangle that stands up out of the plane. You'll need to think a little bit to figure out the lengths of the sides of the box, but it's the same concept used in 2 dimensions, so I trust you'll be able to work it out. The end result is known as the distance formula, and it tells you how to calculate the distance between any 2 points in 3 dimensions. We say that the 3-dimensional distance formula is a generalization of the 2-dimensional distance formula because we can derive the 2-dimensional formula from it. All we would need to do is set both z0 and z1 to be equal to 0, which is saying that we're looking at points on the xy plane. Once we make that substitution, the last term cancels out and we have the 2-dimensional distance formula. Recognizing these relationships helps us to see how our ideas relate to each other, which helps to better understand the material. Once we have this formula, we can use it to construct the equation of a sphere. A sphere is the set of points x, y, z that are a fixed distance r from a specific point x0, y0, z0. The distance r is called the radius, and the specific point that we're measuring from is called the center. All we need to do is convert this sentence into a formula. By convention, we square both sides of the equation because it's easier to square numbers than it is to take the square root, and this gives us the standard equation of a sphere. Again, we can compare this to the 2-dimensional equivalent, which is a circle. In fact, we can line up these formulas and see just how similar they all are to each other. Although we're not going to use it in this class, you should be able to come up with a reasonable conjecture for what this formula would look like if we had a 4th dimension. A common variable choice for that is w, but as the number of dimensions get larger, we often change our labels to being numerically based rather than using more letters. Of course, it's one thing to write down a formula, and it's quite another to try to visualize it. The idea turns out to be related to the topic of the next video, but we'll leave you to explore the 4-dimensional world on your own. When trying to understand the shape of these 3-dimensional graphs, it can be helpful to reduce it back to 2-dimensional shapes. One way of doing that is by creating traces. Here's the definition. Definition: a trace of a function f of 2 independent variables x and y in the x direction is a curve of the form z equals f of x c, where c is a constant. Similarly, a trace of the function f in 2 independent variables x and y in the y direction is a curve of the form z equals f of c y, where c is a constant. This is a lot of words, so what does it mean? Let's focus on the first part. We're evaluating the function along points of the form xc. In other words, we fix the y value, and we're letting the x value be free to move. It's a trace in the x direction because the movement is in the x direction. Notice that the points xc are points along the line y equals c. We are seeing what the function is doing as we move along that line. Another way of saying this is that we're looking at where the surface intersects the plane y equals c. Visually, this picture feels odd because our 2 images aren't lined up with each other. This is just something you're going to have to get used to. You will want to practice visually rotating pictures so that the axes line up. For this picture, if you wanted to make them line up better, you can rotate the 2-dimensional picture so that the positive x-axis points down, which is more like having the positive x-axis pointing towards you. The second part of the definition is the same idea, just with the x-coordinate fixed and the y-coordinate free to move. Notice that we've oriented the 2-dimensional picture in the conventional way, and we'll leave it as a mental exercise for you to line them up. You may want to pause the video for a moment and do that quick exercise. We've actually seen these traces already, but we didn't bring any attention to them. When we were graphing by plotting points, we created a grid of values, and then we also showed a graph of the function. We'll draw on the trace in the x direction along y equals 2 and highlight those values in the chart. The graph has many more points plotted than what the chart shows, but you can see the pattern of values increasing and then decreasing again. You can also see that we can derive the formula for the trace by simply substituting the appropriate value in for y. In the same way, we can do a trace in the y direction by fixing x to be equal to 1. This corresponds to a row of values on our chart. In fact, the graph itself is nothing more than a large collection of traces. You should practice mentally tracing the shapes of the parabolas going in both the x and the y directions. This is a skill that you can develop over time so that you can more easily visualize 3-dimensional graphs. You can further build this intuition by looking at common objects and imagine that you're slicing them into pieces and trying to visualize what each of those slices would look like. All of this helps to build your 3-dimensional visualization skills and intuition. A similar concept to traces is that of a level curve. Traces are what you get when you slice a graph using planes with either the x or the y variable being fixed. A level curve is what you get when you slice a graph using planes with the z variable being fixed. In other words, a level curve tells us all the points on the graph that are at a specific height. This gives us another way to understand the shape or behavior of a function. Here's the formal definition. Definition: a level curve, or a contour, of a function f of two independent variables x and y is a curve of the form k equals f of xy, where k is a constant. This definition actually gives us a method of creating level curves. We simply pick some k values, which correspond to specific heights, and then look at what we have when we set our function equal to those values. Let's look back at the example we used earlier. What is the level curve at height 0? We simply set the left side to 0 and move terms around to get x squared plus y squared equals 4. In other words, we get a circle of radius 2 centered at the origin. Let's look at the trace at height 1. This gives us a circle of radius square root of 3. And at height 2, we get an even smaller circle. When we put these pictures together with a couple more into one graph, we get a contour map. Notice that we've labeled the individual circles so that we can tell which is which. Strictly speaking, the level curves all live on the xy plane, but we can visualize in 3 dimensions to better understand the shape of the surface. All we need to do is raise these curves to the specified heights. And from this, we can start to see the outline of the same shape that we've been looking at earlier. Here it is one more time with the mesh. We can actually understand some of the features of the surface without having to think in 3 dimensions. Notice that in this collection of level curves, the curves get closer together as the value of k gets smaller. The closest of these curves is related to the steepness of the surface. If the contour lines are close together, the graph is steep in that area. If there are very few contour lines, it means it's less steep. A practical application of this is reading a topographical map if you're going hiking. This is a topographical map of the land near Nevada State. The level curves correspond to specific altitudes and can be used to understand the shape of the terrain. Where there aren't many contour lines, the land is basically flat. This region is the part of the land that slowly moves uphill towards the base of the mountains. And over here is Mount Scorpion. We can see that there are lots of contour lines, which makes sense because that's a mountain. The USGS has a wide collection of free topographical maps to look at if you want to know more about the shape of the Earth near where you live. The book ends this section with a collection of graphs that are represented in both 3D and as level curves. It is a good exercise to look at these pictures and practice going back and forth between the 2 pictures. You should also try to think about the shapes of the traces. The online book also provides some links to some web-based graphing tools if you want to explore these things further. Before we can discuss calculus, we need to introduce an extremely important part of the mathematical language called vectors. Vectors are a very general concept that appears in many forms throughout mathematics. For this class, we're going to be sticking to the basic concepts. Definition: a vector is a quantity that possesses the attributes of magnitude and direction. The most basic geometric representation of a vector is an arrow. More formally, these are known as directed line segments, which really just means that the arrows we draw need to be straight. The pointy end is often called the tip, as in the tip of an arrow, and it's sometimes called the head, as in arrowhead. The opposite end is usually called the tail. Notice how an arrow satisfies the property of being a vector. Each arrow has a specific length, which is the magnitude, and each one points in some specific direction. What's important about this is that it gives us the ability to describe when 2 of these arrows are the same. Here are 2 pairs of arrows. In the pair on the left, we can see that they are different because their lengths are different. And in the other pair, the arrows are different because they point in different directions, even though they are parallel to each other. From this, we can intuitively recognize what it means for 2 of these arrows to be equal to each other. They are equal if they have the same magnitude and direction. Notice that this means we don't care about where the arrows are drawn. We are only looking at the magnitude and the direction. We are now going to think about vectors in the context of the xy plane. If we draw an arrow on the plane, we can describe it by measuring how far in the x and y directions you must travel to get from the tail to the tip. For example, for this vector, you move 3 in the x direction and 2 in the y direction. We denote this vector as 3, 2 with pointy brackets. This is known as the component form of a vector, with 3 being the x component and 2 being the y component. It's very important that you use pointy brackets and not parentheses, as this helps us distinguish points from vectors. The point 3, 2 is drawn in exactly one way, but there are many ways that we can draw the vector 3, 2. But just because they aren't the same, it doesn't mean that they aren't related. If we draw the arrow with the tail at the origin, we say that it is in standard position. When we draw the vector AB in standard position, its tip is at the point AB. If we draw the vector that connects the point Q to the point R, we denote this as the vector pointing from Q to R. The notation says this in an intuitive way. If we have the coordinates of the points, we can then calculate this vector by taking the difference. Notice that to get the vector from Q to R, we have to subtract the coordinates of Q from the coordinates of R. This is the ending position minus the starting position. If you're ever not sure which to subtract from which, you can always sketch a simple picture and try it both ways to see which one gives you the correct values. Although we're only working in 2 dimensions for now, vector notation easily generalizes to as many dimensions as we want by just adding in more components. As we've already done a few times in this video, we often use subscripts to keep track of the components rather than introducing more letters, especially when we get beyond 3 dimensions. A quick word about notation. When I write my vectors, I always mark them with a vector symbol above them. The reason is that vectors are a different type of objects than numbers, and this vector symbol reminds me of that. Textbooks tend to use bold-faced fonts for vectors. The reason for this is mostly historical. It used to be very difficult and expensive to typeset vector arrows, but the use of the bold font was readily available as an option. As a student, this always annoyed me a little bit because it was very easy to overlook the bold font, which caused me all sorts of problems. So throughout these videos, I will always use a vector arrow for vectors just to be absolutely clear about what type of object a symbol is supposed to represent. I recommend you adopt the vector arrow for your writing as well. The book has some good exercises to help you build your intuition about what vectors represent and how they interact with each other. We saw earlier how to compare vectors geometrically. 2 vectors are equal if they have the same magnitude and direction. This geometric description is fine for our intuition, but we need to formalize this because while it's good for intuition, it's hard to put into practice in this form. So we will now take a look at that idea from an algebraic perspective. If we represent the vectors u and v using component form, we can see that the only way the vectors are going to be equal to each other is if the corresponding components are equal. Otherwise, either the magnitude or the direction, or possibly both, will not match up. For higher dimensional vectors, we would need all the corresponding components to be equal to each other. The interplay of the algebra and the geometry of vectors will be very important to us as we keep moving forward. And you'll see that we're going to move back and forth between the 2 frameworks in order to make sure that we have a robust understanding of both of them. So far, we've talked about the basic structure of a vector. In the next video, we're going to see how arithmetic and algebraic operations can be applied to vectors. This video is all about performing various operations on vectors, both in algebraic and geometric settings. Please note that I'm doing these sections in a different order than the book. I prefer starting with the geometric approach, possibly because I have a background in physics, and so vectors to me carry physical concepts of velocity, force, acceleration, and other ideas that I find to be geometrically intuitive. For this video, we're going to look at this through displacement. A vector can be thought of as a description of movement. You start from the tail and move to the tip. If we're going to add vectors, we're going to do one movement followed by another. In other words, we perform the motion described by the first vector, and then perform the motion described by the second vector. The question we're trying to answer is, what is the overall movement? In this understanding, to add the vectors, we use the tip-to-tail method, meaning that the tip of the first vector becomes the tail of the second vector. Then the overall movement is the vector that points from the very beginning of the motion to the very end of it. We call this the resultant vector. There's another picture of this that you will see, which is the parallelogram law for adding vectors. For this, you put the tails together and use the vectors as the side of a parallelogram. Then the resultant vector is the diagonal starting from where the tails are joined together. This picture has a number of applications, especially in linear algebra, so it's good to be aware of it. At least for getting started, I found that more students tend to gravitate towards the idea of movement, but it's important to be aware of both. Before we talk about subtraction, we're going to talk about scalar multiplication. The word scalar should remind you of the word scale, which should bring to mind a proportional stretching or shrinking of an object, such as with maps or models being at a certain scale. Scalar multiplication is a matter of stretching the vector along its direction of motion. And for this class, scalars will always be real numbers. So if this is the vector u, then the vector 2u is what you get when you double the length. And 1/2 u has half the length. If we multiply by a negative number, then we stretch by the corresponding value and also flip the direction. With this in mind, to calculate the vector u minus v, we're going to think of it as u plus negative v. Writing subtraction as addition of the opposite is a pattern that goes all the way back to some of your early arithmetic and comes up throughout your study of algebra. So this should feel very familiar and intuitive by this point. To subtract vectors, we flip the direction on the second vector and then add as usual. We've demonstrated that here with the tip-to-tail method. There are other geometric methods out there that do tip-to-tip and other things like that, but I found that students tend to get confused because there are too many different rules to remember. So I think it's best to stick with one method for addition and work with that until you have more experience. Now that we have established the geometric framework, we're going to use that to think through the algebraic framework. Let's draw some vectors on a coordinate grid and write them out in component form. If we were to add them together geometrically using the tip-to-tail method, it would look like this. And if we look at the resultant, we can see that the total x movement is the sum of the individual x movements, and that the total y movement is the sum of the individual y movements. And this observation allows us to write down an algebraic formula for the sum of vectors when they are written in component form. To add vectors in component form, we add together the corresponding components. Using the same idea, we can look at the case of scalar multiplication. If we double the length of the vector, we double both of its components. And this is a general pattern for multiplying a vector by a scalar. Each component gets multiplied by the scalar. In many ways, this behaves like the distributive property, and we'll see more about that later. When it comes to the algebraic manipulation of vectors, there are some important vectors known as the standard unit vectors. These are the building blocks of all our vectors and are an extremely important conceptual and computational object to have. In 2 dimensions, the standard unit vectors are the vectors 1, 0, and 0, 1, which are denoted by I and j. We like these vectors because they allow us to take vectors written in component form and rewrite them using a more natural algebraic notation using some basic vector operations that we've developed. The vector AB in component form becomes AI plus BJ. This manipulation is helpful because the I and j vectors behave exactly like you expect they would with respect to the algebraic operations of addition, subtraction, and multiplication. Here's another way to see that adding vectors should be done component-wise. If we first rewrite the vectors in terms of the standard unit vectors, our algebraic experiences strongly suggest that we combine like terms, and that leads us to the same result as before. This also helps to explain why multiplication by a scalar should distribute across the components. When we write this out in terms of the standard unit vector, it's literally just the distributive property. In 3 dimensions, we have 3 standard unit vectors, I, j, and k. All of the ideas that we developed for 2-dimensional vectors will work with these 3-dimensional vectors. If you can add and subtract 2-dimensional vectors, you can probably figure out how to add and subtract 3-dimensional vectors. You can probably also figure out how to multiply a scalar by 3-dimensional vectors. There are also higher dimensional versions of this, but we're not going to go there in this class. You might have noticed that we didn't talk about division by a vector. It turns out that you will never divide by a vector. We also didn't talk about multiplying 2 vectors together. That one turns out to be a more complicated idea that will have to wait for another section. In the next video, we're going to pick up the idea of the algebraic properties of vectors and investigate the magnitude of vectors. Every time vectors are taught, math professors are obligated to point out that there's a list of algebraic properties of vector operations. These are important because they point to some of the foundations of algebra and place the entire framework of vectors inside a larger narrative of how we do algebra. If you go on to take upper division courses in mathematics, you will almost certainly run into these again. They are very useful in formal proofs and derivations. But at this level, I think the outcome for most students is just to remind you of the names of certain algebraic properties and recognize how these rules reflect the standard rules of algebra that you already have in your experiences. In the previous video, we hinted a bit at these by using your algebraic experiences to do some vector manipulations. This section formalizes all of that into a list of properties. We will go over them briefly and not get bogged down in the proofs and the details. The first two are the commutative and associative properties of addition. These should be very familiar. The third is the existence of a zero vector that functions as the additive identity. The fourth defines the additive inverse. You may not recognize these in this form, but they are a reflection of some of the basic properties of real numbers. Notice how the vector arrow above the zero vector distinguishes it from the number zero. The next two are distributive properties, but notice that one is the distributive properties of vectors over scalars, and one is the distributive property of scalars over vectors. Although they look similar, these two distributive properties are slightly different from each other because they operate on different types of objects. Then we have a property that looks like the associative property of multiplication, except it's technically slightly different because it's a product of two scalars and a vector, not the product of three scalars. The last one is the multiplicative identity property for the scalar 1. You can actually prove all of these by writing out generic vectors in component notation and using component-wise manipulations. The key fact is that once you're working with a specific component, you're just doing arithmetic with real numbers, so that the properties of real numbers apply. But we're going to leave those as exercises. If you intend to go on to take more upper division math courses, these are exercises that are important for you to understand because it will help to develop your intuition and experience for proofwriting. The important thing is not the algebraic manipulation per se, but that you understand what you're trying to accomplish with those manipulations and how you actually do it. When we introduced the idea of vectors by using arrows, we said that the magnitude of a vector is its length, but we never talked about how you would actually compute the length. Fortunately, we have the Pythagorean theorem to help us. If we draw a vector, we can form a right triangle out of it where the legs are parallel to the axes and the vector itself is the hypotenuse. The lengths of these legs correspond to the component form of the vector. Then we can calculate the length of the hypotenuse for the Pythagorean theorem. This gives us a formula for the magnitude of a vector. If we had 3 dimensions, the formula would generalize how you might expect. These formulas should remind you of the distance formula, which could also be used to find the magnitude of these vectors if you're given the coordinates of the tip and the tail. There is a special category of vectors called unit vectors. A unit vector is a vector of length 1. Unsurprisingly, the standard unit vectors happen to have length 1, but they aren't the only ones. There is a unit vector pointing in every direction, and the same is true in 3 dimensions. An important calculation is to find the unit vector that points in the same direction as some given vector. If you are given a vector v and you want to find the unit vector that points in the same direction, you need to scale the vector by the appropriate value so that it has unit length. That scaling factor turns out to be 1 over the magnitude of v. This makes intuitive sense if you think of a few examples. If you have a vector of length 3, how much do you need to shrink it by to make it have length 1? It must shrink down by 1/3, or by 1 over 3. And that's the basic idea. There's an algebraic derivation of this that comes from proving that the magnitude of k times v is equal to the absolute value of k times the magnitude of v. But that's part of one of the activities, and so it's better for you to work that one out for yourself. It's important to have a solid foundation in these basic vector manipulations because we're going to use them throughout the course. It turns out that there are several ways to define multiplication between vectors. In this section, we're going to discuss the dot product. We'll begin with the definition. Definition: the dot product of the vectors u and v in Rn is a scalar quantity u dot v is equal to u1v1 plus u2v2 plus ... plus un_vn. At this point, this is just a formula. We'll talk about how to interpret the values soon. For now, we just want to make sure that you know how to do the calculation. Notice that we are taking the product of the corresponding vector components and then adding the results together. So if we calculate 124.-230, we would get 1 times -2 plus 2 times 3 plus 4 times 0, which is 4. Notice that the output of this is a scalar. For this reason, this is sometimes called a scalar product. The dot product satisfies certain properties. We won't go through the proofs carefully in this video because it's just plugging things into the formula and doing a little algebra. If u, v, and w are vectors in Rn, then the dot product is commutative, it distributes over vector addition, and the dot product has a property that looks similar to the associative property, but technically isn't. Just as with the previous section, These properties point to some foundational concepts that are useful in proofs and derivations, but we're not going to spend time discussing them in the abstract. However, there is one property of the dot product that we will discuss in detail. It turns out that the dot product of a vector with itself is an important quantity. Let's look at the dot product of a two-dimensional vector with itself. After writing it out, we get a result that should seem familiar. You might recognize this as the square of the magnitude. This property holds true in general. The dot product of a vector with itself will always give you the square of the magnitude of the vector. This fact is used very frequently when working with vectors, especially in proofs and derivations, so it is important to have this fact at your fingertips. Now that we have a few facts about the dot product, let's take a look at what it means. The best way to do this is through the derivation of a geometric property of the dot product. If we have two vectors with their tails together, they will form an angle that is between 0 and 180 degrees. We'll call that angle theta. By connecting the tips of the vectors, we create a triangle. We'll leave it as an exercise to convince yourself that the third side of the triangle is the vector u minus v if we draw the arrow from the tip of v to the tip of u. Now we have a triangle with all three sides and one angle labeled. This is a situation where we can apply the law of cosines. The law of cosines uses the squares of the lengths of the sides, which we can rewrite using the dot product. Notice that in the difference term, we have to use the distributive and commutative properties of the dot product to move forward. From here, we can do some canceling and rearranging to simplify the equation. You can pause and look at the details, or find the details in the book, but they're not difficult manipulations. It's just following the algebra. In the end, you get this formula. The dot product of the vectors is equal to the product of the lengths of the vectors multiplied by the cosine of the angle between them. This is often written in two other forms, solving for either the cosine of the angle or the angle itself. This shows us that the dot product is related to the angle between the vectors, and we even get an explicit formula for the angle. It's important to remember that this is the formula for the angle between the vectors when they are drawn with their tails together. There are many errors that can result from not checking that. Let's take a closer look at the dot product formula. Notice that if the angle is pi over 2, then the dot product is going to be 0. In other words, if the vectors form a right angle with each other, then the dot product is 0. There's a special term we use for this. Two vectors are said to be orthogonal to each other if their dot product is 0. For this class, we can use the words orthogonal and perpendicular interchangeably, but there are other applications of vectors for which the word perpendicular ends up being geometrically confusing. And so the preference when working with vectors is to use the word orthogonal when the dot product is 0. We can actually discover more about the dot product from this formula by thinking about the behavior of the cosine function for different angles. Notice that if the angle is acute, then the cosine is positive, which then means that the dot product is positive. If the angle is obtuse, then the cosine is negative and the dot product is negative. This means that the sign of the dot product tells us whether the angle between the vectors is an acute angle, a right angle, or an obtuse angle. This is a useful algebraic tool to have when thinking about the geometry of vectors. For the next video, we're going to look at some applications of the dot product. One of the more practical applications of vector concepts is in the study of physics. Students often lose sight of the fact that Newton invented calculus in the process of trying to understand physical motion. So we will be taking a short tangent into physics to see how these ideas can be applied. Specifically, we're going to explore the concept of work. There are two vector quantities that are relevant to this topic: displacement and force. Remember that displacement is the relative motion of an object. When we were adding vectors, we thought of the sum of vectors as indicating one movement followed by another movement. Those movements are displacements. Notice that they have both a magnitude and a direction. The idea of a force is a push or pull applied to an object. When you bring magnets together, they generate a force that either tries to pull them together or push them apart depending on the polarity. Gravity is a force that pulls objects together. Notice that forces are also vector quantities because there's a magnitude and a direction. As you bring magnets together, the direction of the force on each magnet is either towards or away from each other, and the force gets larger as they get closer together. It should hopefully make intuitive sense that applying a force to an object can lead to its displacement. Work is a measure of the energy used when applying a force to displace an object. As we are applying the force to the object, we are causing the object to move, and the work is the conversion of the applied force to the kinetic energy of the object. There's obviously a whole lot more we can say about this, but that's the extent of the intuition that we're going to develop for this course because we were going to consider only very basic cases. The formula for work turns out to be a dot product. Work is force dot displacement. Once again, notice the vector symbols over F and D, but not W. Work is a scalar quantity. The reason for the dot product is related to the fact that only the part of the force in the direction of motion counts as far as energy transfer is concerned. If we are pushing a cart along a track, we do a better job of putting energy into the cart if we push parallel to the track instead of at an angle. The more the force aligns with the motion, the more energy is transferred. When solving one of these work problems, you will want to draw a picture to help identify the force and the displacement. From there, just take the dot product of the vectors. Depending on the problem, you will either use the geometric formula or the component-wise algebraic formula. A common error that students make is that they do not put the tails of the vectors together when they calculate the angle. The activity for this section provides a little bit more insight into the concept of work, so you should definitely take the time to think about that one. Let's take another look at pushing the block around the track, but pushing at an angle. If we think about it, the only part of our force that is doing any work is the part that's parallel to the track. There's another part of our force that is perpendicular to the track, and it's doing nothing useful at all. And this hints at the usefulness of breaking a vector down into two separate pieces that reflect the underlying problem, where those two pieces are either parallel or perpendicular to a specific direction. In this problem, we're looking at the direction of motion, but this can apply to any direction that's relevant to the problem. The projection of the vector u onto v is the part of u that points in the direction of v. Here's a diagram that indicates how the projection is determined, and we'll look at the details of this briefly. The notation is slightly cumbersome, but it is a fairly common notation. Notice that the vector we project onto is a small subscript to the PROJ. We've put a vector arrow over this because it's a vector. Very few books do that, and it honestly looks kind of ugly. But I think the emphasis is more important than the aesthetics. For the part that is perpendicular, we use this notation. You might remember this symbol from a geometry class, and it represents perpendicularity. So this is the projection of u onto the direction perpendicular to v. And this quantity is also a vector, so it also has a vector arrow. The geometry of a projection can sometimes be difficult for students to visualize and draw. So we're going to describe it in a very prescriptive way that helps to avoid errors and do a couple examples. When drawing the vector projection of u onto v, first draw the two vectors with their tails together. If you can, draw v a little bit lightly so that it doesn't become a distraction later. Then extend the vector v into a line. Draw a line from the tip of u to the line you just drew so that the two parts are perpendicular to each other. The projection of u onto v is the vector that points from the tails to the point of intersection. Here are some pairs of vectors u and v. You should pause the video and see if you can visualize how to construct the projection of u onto v for each pair. In each of these cases, you're starting off with step 1 already done for you. Extend the vector v into a line, find the correct perpendicular, and use the intersection point to create the projection. Here are the results. Notice that in some cases the projection vector points in the opposite direction of v. Also notice that one pair has the labels u and v swapped, and they give different results. This emphasizes the importance of knowing which vector you're projecting onto which. The reason I teach students to draw the line through v is because some students turn their pictures into triangles by connecting the tip of u to the tip of v, and that leads to problems. It also deals with the case when u and v point in opposite directions, which is also a source of confusion. By drawing the extension explicitly, I have found that students make those errors much less often. The derivation of the formula is in the book, and you're encouraged to work through that yourself. It's just a quick exercise in applying the properties of the dot product. There's another way of writing this vector that provides a little more insight. Notice that in this second form, we have written it as a product of a scalar and a unit vector in the direction of v. The scalar is called the component of u in the direction of v. Notice that if the component is negative, then the projection points in the opposite direction of v. Lastly, we can get the perpendicular projection by manipulating the definition and making a substitution. I find it's much easier to think of this relationship in solving for the perpendicular projection rather than memorizing the final formula. As a general rule, I recommend against memorizing formulas, because they often do not increase your level of understanding, and you won't know that you don't understand until several sections down the line, and at that point, you're stuck trying to play catch-up. Vector projections are important for multivariable calculus, so it is important that you are conceptually and computationally fluid with them. Make sure you take the time to do the exercises in the book to make sure that you're where you need to be with this topic. The cross product is the second of two different types of vector products that we have in multivariable calculus. Unlike the dot product, the result of a cross product is a vector and not a scalar. We also only define the cross product for three-dimensional vectors. There is a way to generalize this to higher dimensions, but that goes beyond this course. The book introduces the cross product on the standard unit vectors in R3. The key fact is that we use the right-hand rule on a right-handed coordinate system to derive these values. The first term of the cross product is the index finger, the second term is the middle finger, and the result is the thumb. If we swap the order, then we have to turn our hand upside down to swap the positions of our index and middle finger. When taking the cross product of two different standard unit vectors, the result will always be plus or minus the third. The results listed here are in a slightly different arrangement than the book because I wanted to point out a pattern. All the positive results come from taking the letters in the cyclic pattern I, J, K. I cross J equals K, J cross K equals I, and K cross I equals J. All the negative results come from going in the reverse order. And so if you just remember that cyclic alphabetical order gives positive values and reverse cyclic alphabetical order gives negative values, you'll have a much easier time remembering the results. If we use the distributive property and these formulas, we can come up with a general formula for the cross product. The calculation is just algebra and these formulas, and the book has worked it out in detail for you. We're going to jump straight to the result. Definition: the cross product U cross V of the vectors u and v in R3 is the formula u2v3 minus u3v2i minus u1v3 minus u3v1j plus u1v2 minus u2v1k. The formula looks messy, and in this form students often overlook the negative sign in front of the middle term. There are matrix formulations of this that are much easier to remember. Notice that in the bottom form, the middle row is the first vector, and the bottom row is the second vector. If you haven't worked with determinants before, it's okay to think of these as just the special notation for a specific calculation. We're going to skip ahead and talk about the physics concept of torque in order to build up further insight before talking about the geometry of the cross product. Torque can be thought of as a twisting force that is trying to cause something to rotate. Imagine that you're trying to tighten a bolt with a wrench. Where would you want to push on the wrench to make sure it's tight? If you have any experience with this, you would almost instinctively push further away from the bolt. This shows that torque depends on both the force you apply as well as where you apply it. But it also depends on the angle that you're applying the force. If you're pushing inward or outward, you're applying an unhelpful force. This is similar to pushing in a direction perpendicular to the direction of motion in a work problem. The amount of torque you get is dependent upon those three factors: the size of the force you're applying, the angle at which you're applying the force, and the location that the force is being applied. Here is the formula for torque. In this formula, the fancy T is the Greek letter tau, and that stands for the torque. R is a vector that points from the axis of rotation to where the force is being applied, and F is the applied force. Since the cross product is a vector quantity, we have put a vector symbol over tau. Be careful that when you're computing the cross product that you put the tails together. It is very common for students to just use vectors in the diagram without paying attention to this, and this can lead to getting the direction wrong. I want to take a moment to point out the differences in the book so that you know where they are. The book uses torque is equal to F cross R instead of R cross F. In the book's diagram, the vector R is backwards from the convention, pointing from the place the force is being applied back to the axis of rotation. It turns out that these two differences cancel each other out, and the curious student may want to think about how they might verify that for themselves. The third difference is that the angle theta is not the conventional angle between vectors, which is the angle formed when the tails are put together. For various formulas involving the sign of this angle, it turns out it doesn't matter and you'll get the same result by following the book's presentation. So there's nothing mathematically wrong with the book, it's just different from the physics conventions. Similar to the work problems with dot products, we're only going to look at the most basic applications, so at some level it doesn't even matter which way you do it. If you do look up more information and go deeper into the topic, you're likely to see other formulas for torque. Here are just some possibilities. The first equation is the standard version for physics using vectors. The second equation involves a concept known as the lever arm or the moment arm. We're not going to define it here because it's not relevant to this class, but you should be careful because this value may not be what you might intuitively guess it is. So be extra careful with that one. The third one is actually related to something we're going to see in the next video, which is why I'm including it here. For this class, we care about the vector form the most because we're getting practice with vector calculations. An interesting conceptual piece of this is that the direction of torque corresponds to tightening or loosening screws. Most of the screws you interact with are right-handed screws. If you're familiar with righty-tighty and lefty-loosey, that's a right-handed rule. If you're tightening a screw, the torque points inward, and if you're loosening the screw, the torque points outward. You will sometimes see these symbols for vectors pointing directly in or directly out of the page. You should think of the cross as the fletching of an arrow, which are the feathers or plastic parts on the tail end. And this dot should be thought of as the tip of the arrow pointing out at you. It's important to know that there are left-handed screws and threads that do the opposite of this, so it isn't some rule that all threads have to behave this way. But the overwhelming majority of the screws that you will run into are designed like this. In the next video, we're going to take a look at the geometry of the cross product. The cross product was defined to be a vector. Remember that vectors are quantities that have both a magnitude and a direction. We're going to start by looking at the magnitude. The algebra for this is neither pretty nor insightful, but fortunately the book shows you all the steps. We're going to go straight to the result. The magnitude of u cross v is equal to the length of u times the length of v times the sine of the angle between them. Again, the angle between vectors is defined to be the angle created when the tails are put together. We're going to focus on the consequences of this formula. The first thing to notice is that if we combine the length of v and sine of theta into a single term, we end up with something geometric. If we draw out the vectors like this, it turns out that the length of v times sine theta gives you the distance from the tip of v to the line formed by u. The same thing works if we combine the length of u with sine of theta instead. If this feels kind of like what we did with vector projections, that's because it is similar to vector projection. The difference is that with vector projections, we usually didn't have the angle theta in hand, and so we would have to use the dot product to go get it, and that would end up being a bunch of extra steps. But there are definitely some geometric relationships here that are interesting to explore. But back to the cross product. If we draw out the parallelogram formed by the vectors u and v, we can see that the length of the cross product corresponds to the area of the parallelogram. We're going to use this fact much later in class, so don't lose track of this relationship. We can also draw a triangle by connecting the tips of the vectors, and the area of this triangle is half the length of the cross product because it's half the area of the parallelogram. This will be helpful when working through some of the exercises. There's a special case of the area picture, which is when the two vectors are parallel to each other. We can think of this as the area of the parallelogram collapsing to 0, which would make the magnitude of the cross product equal to 0. Students sometimes get worried when they get a 0 because they think they did something wrong. Getting a 0 here does not automatically mean you made a mistake. It just means that the vectors are parallel. So now that we know about the magnitude of the cross product, what about its direction? It turns out that if you calculate u dot u cross v and v dot u cross v, you will get 0. The book shows the details of this calculation. If the dot product of two vectors is 0, then the vectors are perpendicular. This means that u cross v is perpendicular to both u and v. Notice that if u and v are not parallel to each other, then together they define a plane. There are only two directions that are perpendicular to the plane, and the correct one is the one that follows the right-hand rule. Try to match your hand to this diagram. Point the index finger of your right hand to the right, and point your middle finger at the screen. Then your thumb should match the black vector. If the vectors are parallel to each other, then the cross product is 0. From the previous section, we know that the magnitude of the cross product of parallel vectors will be 0, and so that makes the direction irrelevant. But with this new perspective, we can see that two parallel vectors don't even form a plane, so it doesn't make sense that there would be one particular direction for the cross product to point. The result is simply that you get the zero vector. It's sometimes the case that we use the vector n to talk about a vector that's perpendicular to a surface. N stands for normal, which in this context just means perpendicular to the surface. The vector n is usually a unit vector, so you often hear it referred to as the unit normal vector. And so with this, we get another formula for the cross product. The vector n is implied to be the normal to the plane formed by u and v following the right-hand rule. Notice that this formula isn't saying much more than the previous formula. The normal vector is just saying what direction the cross product points, and the length is the same value we saw earlier. But the addition of this direction does create a three-dimensional picture for us that we didn't have when we were just looking at the magnitude. With two vectors, we can form a parallelogram. Notice that this is a flat object. With a third vector, we can get a volume by branching out into a third dimension. The use of three vectors forms a parallelepiped. This is just the natural generalization of a parallelogram. It can be thought of as a box with slanted sides. We can calculate the volume of a parallelepiped by using the cross product and the dot product together. The volume of the parallelepiped formed by the vectors u, v, and w is the absolute value of u cross v dot w. We won't go into the details, but the idea is that the u cross v part gives us the area of the parallelogram that makes the base, and then the dot product of the unit normal vector with w gives us the height. While this formula is useful and uses the concepts and formulas in the last couple sections, it's not important to this class, so it's probably not one that's worth memorizing, even though it's not a difficult one to remember. If you bump into an application of it down the line, you can always look it up then. The book has a brief section that talks about the similarities and differences between the dot product and the cross product. It's worth thinking through this to help the ideas sink in more deeply. The dot product results in a scalar, and the cross product results in a vector. The dot product is commutative, but the cross product is not. Technically, we would say that the cross product is anti-commutative or skew-commutative because you get the negative result when you swap the order. The dot product is related to the cosine of the angle between the vectors, and the cross product is related to the sine of the angle between the vectors. We can see that these formulas are otherwise very similar to each other. If the dot product is 0, then the vectors are orthogonal to each other. If the cross product is 0, then the vectors are parallel to each other. Recognizing these four properties helps us to see how these two products are both similar and different. You will want to be very familiar with all of these properties. As we continue expanding our perspective of three-dimensional space, it makes sense that we should spend some time thinking about some basic shapes. One of the most basic shapes to work with is a line. In 2 dimensions, we often represented the equation of a line using slope-intercept form. If we think about graphing a line from this equation, the intercept gives us a starting position, and the slope gives us a direction. While it may seem simple, this framework turns out to be useful for thinking about lines in 3 dimensions. We'll begin by looking at the definition. Definition. A line in space is the set of terminal points of vectors emanating from a given point P that are parallel to a fixed vector V. At first, this may feel nothing like what we just did, but a picture will be helpful. Here's a point P and a vector V. We want to draw the terminal points of all vectors that emanate from P that are parallel to V. Here are some examples. We should also include vectors that are parallel but point in the opposite direction. Notice how all these points form a line, and that this line is parallel to V. For this reason, V is called a direction vector. If we wanted to describe how to get to any of these points starting from the origin, we would first have to move to the point P, and then move by some scalar multiple of V. And this is exactly the vector form of a line. Notice that there are multiple representations of a line. We can change the point P to any other point on the line, or we can change the length of V or have it point in the opposite direction. So the equations of lines are not unique. The vector form of a line is called that because it's written as a vector equation. If we wanted to look at the individual components of a vector, we would have a set of parametric equations for the line. Both representations carry the same information, so the only difference is in how they look. We'll start with the vector equation. We're going to write this in terms of components. The vector r of t is a function with three components, which we will call x of t, y of t, and z of t. Notice that each coordinate is itself a function of t, since all the coordinates are subject to change if we change the value of t. We can call the starting position vector x0, y0, z0, and the direction vector a, b, c. By plugging this in and doing some algebra, we get this equation. Remember that two vectors are equal when each of their corresponding components are equal, so we can turn this one vector equation into three equations. The collection of these equations is called the parametric equations of a line. The three equations come together as a package so that the whole collection represents the line and not any individual part. Notice that if we have the parametric equations of the line, we can put them back together into a vector to get a vector equation. So they really are the same thing. We're going to spend a moment to look at the general idea of parametric equations. Parametric equations are equations that are related to each other through external variables called parameters. A line is a collection of coordinates using the variables x, y, and z. The external variable for these equations is t. The idea is that this one variable controls the three coordinate variables. For every real number t, you get a point on the line. For example, when t equals 0, you get the point x0, y0, z0. As t increases, we move further along the line in the direction of v. As t decreases, we move along the line in the opposite direction of v. In some sense, the parameter t controls where along the line your point is located. In fact, if we vary t smoothly, we would trace out the entire line. In lots of applications, we think of t equals 0 as the starting time of some activity, so it should not be confusing to think of x0, y0, z0 as the starting point. Continuing along with the time analogy, as time increases, we can imagine ourselves walking along the line at a constant speed in the direction of v. For negative values, we simply think of that as winding time backwards and think about where we would have been had we been traveling along the line at a constant speed before t equals 0. The line itself is the set of all points that we visit along this path. When we think about the intersection of lines, we're thinking about whether the two paths intersect, not whether the people moving along those lines actually get to meet each other. We use two different parameters when talking about two different lines to remind us that the parameters are independent of each other. So for the first line, we may be at the intersection at t equals 1, and for the second line, we may be at the intersection at s equals 2, and we would still say that the two lines intersect each other. In some situations, you will need to find the equation of a line. Just remember that you need to identify a point on the line and a direction vector. The exact method you use to find those will vary from problem to problem. It can be helpful to sketch a picture sometimes to help visualize the situation. But in the end, you just need two pieces of information, a point on the line and a direction vector. In the next video, we're going to take a look at the next step up from lines in 3 dimensions and try to understand how to describe planes in 3 dimensions. The definition of a plane that we're going to use looks very similar to the definition of a line. We're going to put the definitions side by side to show the similarities and talk a little bit about mathematical language before taking a deeper look at planes themselves. A line in space is the set of terminal points of vectors emanating from a given point P that are parallel to a fixed vector V. A plane in space is the set of terminal points of vectors emanating from a given point P0 that are perpendicular to a fixed vector n. As you get further along in math, definitions become more and more important as the foundation of how you think about things. It's very important that our definitions are as precise as possible so that the rest of our ideas can also be as precise as possible. When you think about definitions in this way, you can start to get a sense of the flow of the language, which not only helps you to think about definitions, but also theorems and proofs. The first line is stating the name of the object being defined. The second line describes the type of object that is being defined. In this case, it's a set of terminal points of vectors. The remainder is a set of descriptive phrases that describe the property of the object being defined. What do we know about these vectors? They emanate from some point and have some relationship with another vector. Understanding this framework will help you organize the information in your head to make it easier to remember and less prone to error. and that can be very helpful in being successful in a math course. But at this specific moment, it's probably not of central importance that you make this connection. As you keep studying math, you will find that it's useful to slow down and make sure you're starting to catch some of these higher level patterns in how we do math, as it will help you understand what's happening at a deeper level. But for now, we'll return to thinking about the definition of a plane. Definition: a plane P in space is the set of all terminal points of vectors emanating from a given point P0 perpendicular to a fixed vector n. Let's start with the point P0 and draw the vector n emanating from it. Technically, n can be anywhere, but the picture is simplest to visualize if we draw it this way. Let's think about all the other vectors that emanate from P0 that are perpendicular to n and plot their terminal points. For example, there are a bunch of points in this direction. And we can actually think about this as an entire line of points. We can then imagine rotating this line around the vector n to get another line in a slightly different direction. In fact, we can keep on rotating this all the way around, and as we do this, you can see that a plane is being created. To get from the picture to the formula, we're going to use the fact that the dot product of two vectors is 0 when those vectors are orthogonal to each other. We are given the vector n, which we will write as ABC, and we need to get the vector that points from P0 to some point P on this plane. We will call the coordinate of P0 x0, y0, z0, and a generic point P on the plane x, y, z. Remember, to get the vector from one point to another, we need to subtract the coordinates. So the vector P0 to P is x minus x naught, y minus y naught, z minus z naught. We then substitute and take the dot product, which gives us an equation of the plane. We call this final version the scalar equation of the plane, and we call the original vector form the vector equation of the plane. This is similar to the parametric form of a line and the vector form of a line in that they are both representations of the same thing. The conversion backwards from the scalar equation is a bit more complex this time, but if you remind yourself that it's a dot product, you should be able to learn to recognize it. Just as we often need to find the equation of a line, we're going to need to find the equation of a plane. And similar to finding the equation of a line, to get the equation of a plane, you need two pieces of information: a point on the plane and a normal vector to the plane. There are lots of different ways to get those two pieces, but those are the two pieces you need to be looking for. A common example of this is determining the equation of a plane that passes through three non-collinear points. What's interesting about this problem is just how many different ways you can do it. All you need is a point on the plane and the normal vector. You start off with 3 points on the plane, and it doesn't matter which one you pick because they're all on the plane. So just pick one and move on to the normal vector. How can we get a normal vector to the plane? By taking the cross product of any two vectors that lie on that plane. This is because the cross product of two vectors is orthogonal to both of the vectors you started with. With these 3 points, you can make 6 different vectors that lie in the plane: PQ, PR, QP, QR, RP, and RQ. And as long as you pick 2 that aren't parallel to each other, you can take the cross product to get a normal vector. Once you make these calculations, you just plug it into the formula. The book has an exercise where you do this, and you should take the time to go through it. This section was relatively short and conceptually simple. However, we're going to come back to these basic skills of finding lines and planes often in this course, so you want to take the time to really understand the ideas that we've discussed. Earlier, we saw how we could get the equation of a line in space by using vectors. We had one vector to move to a starting point, and then we had a direction vector that was scaled by a parameter t that moved us to some other location along the line. The idea of using the terminal point of a vector to plot a curve is what we're going to explore in this section. When we were graphing lines, we thought of it as walking along a straight line path at a fixed speed. But it doesn't have to be this way. For a general curve, the path we travel can go in different directions and can move at different speeds. We will still maintain the idea that for every value of t we're in a specific location, and that this location is the terminal point of some vector in standard position. In the abstract, this idea is just having each of the 3 coordinates being a function of t. For any given t, we have an x-coordinate, a y-coordinate, and a z-coordinate. The equations for these coordinates are called parametric equations, and we would say that we have a parametrization of the curve. We can put the whole thing into a vector r, so that r of t is equal to x of t, y of t, z of t. This would give us a vector-valued function. The input is a number t, and the output is a three-dimensional vector. Alternatively, we can keep the equations separate and have parametric equations. Here are the formal definitions for these ideas. Definition: a vector-valued function is a function whose input is a real parameter t, and whose output is a vector that depends on t. The graph of a vector-valued function is the set of all terminal points of the output vectors with their initial points at the origin. Parametric equations for a curve are equations of the form x equals x of t, y equals y of t, and z equals z of t that describe the xyz coordinates of a point of a curve in R3. Notice that the set of parametric equations automatically gives us a vector-valued function, and that a vector-valued function can be turned into a set of parametric equations. When we are looking at parametric equations, it's important to recognize they have both the shape of the curve and also how we traverse the curve. Even for a curve as simple as a circle, we can have a number of different starting points, we can go in different directions, and we could go at different speeds. Activity 9.6.2 explores this idea more deeply. And in the next section, we're also going to look at the concepts of the velocity and the acceleration of a particle moving along a path, given by a set of parametric equations. But for now, it's enough to know that it's not just the shape of the curve, but also how you travel along it. It is helpful to introduce parametric equations because it gives us access to a wider collection of curves than functions. You might recall using the vertical line test to determine whether a graph is a function. The idea is that we're using the x-coordinate as the input of the function, and that for each input we can only have one output. When we're using parametric equations, that is not a problem. This is because we're not using the x-coordinate as the input, but some parameter t. This also means that we can have curves that self-intersect, and this still isn't a problem. If we wanted, we could take a function of the form y equals f of x and turn it into a vector function t f of t. This is really just a different way of notating the coordinates of a position on the graph as a vector instead of as a point. As a side note, some students write x f of x instead of introducing a parameter. This is a problematic notation. The problem is that we are using the same symbol for two different things. If you look at the graph on the left, the idea becomes more clear if we actually label the axes. We can now see that x is trying to perform two different functions, and it can be confusing. In general, we try to avoid using the same symbol to represent two ideas at the same time. Traces and level curves are two examples of curves that we can convert to vector functions. Just as before, these curves can help us to understand the shape of a surface. Here's the formal definition again as a reminder. Given a function z equals f of xy, we can get a trace by fixing one of the independent variables to be constant. Notice that if we do this, then the function z becomes a function of a single variable, which we can then convert into a vector function. And remember that if we have a vector function, we also get a set of parametric equations. Level curves are more difficult because you may have to identify the parametric equations yourself. This will take some time and practice, but the problems at this level are not too difficult. If your curve is a line or a function of a single variable, then you can use the ideas that we've already seen. The other important curve you'll need to recognize is a circle. The most common two-variable parametrization of a circle of radius a is r of t is equal to a cosine t, a sine t, for t between 0 and 2 pi. This travels once around the circle, starting from the positive x-axis and moving in the counterclockwise direction. Although this is a two-dimensional curve, it can be converted into a three-dimensional curve in several ways. For example, if we picked a fixed z value, such as k, then we would be plotting the circle of radius a at height k. But there's much more you can do with this. For example, the circle of radius a on the yz plane can be obtained by setting the x-coordinate to 0 and picking the y and z coordinates to be the sine and cosine terms. If you wanted to translate the center to a different position, you could just add or subtract constants as appropriate. But these are all just adjustments to a basic picture. Again, this takes a little bit of time and practice. You shouldn't expect to understand this by just watching a quick video. You may find it helpful to play around with some online parametric graphing tools to help you get a little more intuition with this. Let's do a quick review of the derivative from single variable calculus. The goal is to find the slope of the tangent line to a curve at a specific point. The problem is that we need 2 points to apply the slope formula, and this only gives us 1. So we get at it by taking a second point on the curve and using that as an approximation to the tangent, then bring those points closer and closer together. We called that process a limit, and that's what gave us the formula for the derivative of a function. When transitioning to vector-valued function, the formula doesn't change very much. Definition. The derivative of a vector function r is defined to be this formula for the values of t at which the limit exists. We also use the notation dr dt and ddt of r of t for r prime of t. We will look at the computational consequences of this formula later. For now, we'll focus on the geometry of the formula. The vector r of t plus h minus r of t is the vector that points from r of t to r of t plus h. So the derivative captures the direction of movement between these points. Remember that this is being divided by h for small values of h, so this will stretch out the vector beyond those 2 points. And we're taking the limit as h goes to 0, just as before, which is bringing us closer to the tangent vector. And that is exactly what the derivative of a vector-valued function represents. The derivative is the tangent vector to the path. Since physics is one of the main applications of vector calculus, we're going to do a quick review. In physics, we can talk about the position of an object by using a vector. The idea of velocity is how quickly your position is changing with respect to time, so the derivative of position is velocity. Acceleration is the change of velocity. Intuitively, if you're speeding up, then your velocity is increasing, and if you're slowing down, then your velocity is decreasing. Speeding up and slowing down are accelerations, and acceleration is the derivative of velocity. It's very important to remember that position, velocity, and acceleration are all vectors in this context. They have both a magnitude and a direction. This is different from speed, which is the magnitude of the velocity vector, and it is a scalar quantity. You need to be careful with these, as it is common for people to use velocity and speed interchangeably depending on the specific context. So just be aware that you will have to pay attention to the situation and not blindly rely on formulas to get yourself through. The formula that we saw earlier shows that the derivative of a vector-valued function is calculated component-wise. The logic for this is much easier to see if we write the vector r using standard unit vectors. If r of t is equal to x of ti plus y of tj plus z of tk, then the derivative is x prime of ti plus y prime of tj plus z prime of tk for those values of t at which x, y, and z are differentiable. This should be intuitively true if you just notice that the vectors I, j, and k are constants. With that observation, the x, y, and z functions are just being multiplied by a constant, and those constants can be pulled out when taking the derivative. And if you look at the formal derivation in the book, that's exactly what happens. Because of this, the properties of the derivatives of vector functions will feel very familiar. The derivative of a sum of vectors is the sum of their derivatives. This is exactly the same thing as we saw in single variable calculus. The derivatives of products work out to behave like the product rule, even when taking derivatives of dot products and cross products. The reason for this is that if you look at the formulas for the dot product and the cross product, you will see that you end up with a sum of a bunch of terms that are just the product of 2 functions at a time. And that's where the standard product rule shows up to create the pattern in the final results that we see here. With the chain rule, the standard unit vectors can be pulled out, and you're left with the chain rule for single variable calculus. You really ought to take the time to prove these for yourself. Just start by writing r as the sum of its components with the corresponding unit vectors, and see where the manipulation takes you. This usually feels a bit clumsy at first, and that's just from a lack of experience. The best way to get experience is to do the calculation yourself and see how the pieces come together. One of the big applications of single variable calculus is finding the tangent line to curves. Let's review. If we graph the function y equals f of x, we get a curve. If we pick a specific value of x, say x equals a, then we can plug that in to get a point along the graph. The derivative at that point gives us the slope of the line. To get the full equation of the line, we start from the point-slope form and plug in the values, and after a couple algebra steps, we get the equation of the tangent line. The book calls this L of x, and is often called the linear approximation of f at a. We can do the same thing to curves in 3 dimensions. Remember that we need 2 pieces of information to get the equation of a line, a point and a direction. If we pick some specific value of the parameter, say t equals a, that will give us the location of a point on the curve. And then we can use the derivative of the vector function to give us the direction vector. Instead of using point-slope form, which only applies to lines in the plane, we use the vector form of the line. We're using the parameter s instead of t for now to emphasize the idea that the parameterization of the tangent line can be done independent of the parameterization of the curve. We can plug in the point and the direction vector, and that gives us a parameterization of the tangent line. In this form, setting s equals 0 gives us the point on the curve, and there are many situations where this is useful. However, there are times when it's more useful to parameterize the curve so that s equals a gives us the point on the curve, which requires a slightly altered parameterization. In some ways, this is the more intuitive result because it means that the parameterization of the tangent line makes it so that the curve and the tangent are parameterized to meet up exactly at the point of tangency. Notice that this second form looks a lot more like the equation for the tangent line from single variable calculus, which is another reason why this form is often preferred. In the next video, we're going to take a look at integrating vector functions and look at some more physics. In the previous video, we talked about taking derivatives of vector functions. The natural follow-up to that is integrating vector functions. Recall that integrals and derivatives are basically inverse operations of each other. One way to say this is that if capital F prime of x equals little f of x, then capital F of x is the integral of f of x dx plus c for some constant c. While integration can be interpreted as the area under a curve, it will be better for the moment to think of it as the antiderivative. It's just a function that has this special derivative property. The concept of area doesn't quite extend to vector functions in a simple analogous way. But with that caveat in place, here's the definition. Definition: an antiderivative of a vector-valued function little r is a vector-valued function capital R such that capital R prime of t is equal to little r of t. The indefinite integral of little r of t is the general antiderivative of little r, and represents the collection of all antiderivatives of little r. The last part of this statement is a reference to the constant of integration, which will also appear when integrating vector functions. There is not a single antiderivative, but an entire family of them. Just with derivatives, integrals are performed component-wise. The logic is the same, as the standard unit vectors can be factored out of the integrals. The key difference to notice, compared to single variable calculus, is that the integration constant is a vector, which means it will have 3 components. In other words, since there are 3 separate integrals, you will get 3 separate constants of integration, corresponding with each dimension. The most important application of derivatives and antiderivatives is in the relationship between position, velocity, and acceleration. Earlier, we talked about how you can start from the position vector of an object, take its derivative to calculate the velocity, and then take the derivative again to calculate the acceleration. Antiderivatives allow us to undo this pattern. If we're given acceleration, we can integrate it to get velocity up to a constant, and then integrate it again to get position up to another constant. These constants are often called initial conditions. With any one of these vectors and the right number of conditions, we are able to calculate all the others. We are going to apply these ideas to the problem of projectile motion. This is the theoretical motion of an object that is launched under the influence of gravity. What does this mean? Here's how we're going to set up the problem. We are going to work in 2 dimensions, with x being horizontal and y being vertical. The object is launched from the position x0, y0. The initial speed is v0, and the object is launched with an angle theta with the horizontal. The acceleration is the vector 0, negative g. Notice that this is saying that gravity is pulling in the negative y direction. We are going to ignore all the forces except for gravity, so there's no friction and there's no wind. This is a lot of little pieces of information, so we'll start by making a quick diagram of this to guide us as we work through the problem. We are in 2 dimensions. The object is launched from the position x0, y0. The object is launched at a speed v0 at an angle theta with the horizontal. The acceleration is 0, negative g. Since we know the acceleration, we can integrate that to get velocity. Notice that we need to solve for the constants of integration, which we have called v0x and v0y. To do this, we draw a right triangle with the initial velocity so that we can get the x and y components of it. We can plug this in to get the full equation for velocity. Then we can integrate this to get position. Notice that theta is a constant, so the sine and cosine terms are just constants with respect to t. It turns out that once you integrate and solve for the constants, you'll get this result. And this result is the equation for projectile motion. This is the type of calculation that you ought to be able to do on your own. By that, I mean you should be able to work with just these assumptions and arrive at the appropriate equation for the motion of a projectile. In some ways, I hope that if you have a projectile motion problem, that you will be able to derive your solution from first principles rather than just plugging values into this formula. I think you stand to gain so much more from the experience of working it out a few times than you do if you just jump straight to the formula. And that brings us to the end of this section. As always, please take the time to do the exercises and make sure that you understand what's happening in this section. Specifically, by this point, you should be very comfortable with vectors, vector notation, and vector operations. From here forward, when we need to use vectors, we're just going to use them without doing a big review of them. This section is important not so much for the formulas that we derive, but for the logic behind those formulas. One of the big ideas of integration is that you have some quantity that you're trying to find, and you're going to get it by adding up a bunch of really small pieces that approximate the whole thing, and then take the limit as we increase the number of pieces. We see this when thinking about the area under a curve. We approximate the area with rectangles, and then increase the number of rectangles to get better and better approximations. This limiting process becomes an integral, which we can think of as a sum of infinitesimal pieces. It turns out that we could do this with a huge variety of objects. Arc length can be thought of as the distance you travel if you travel along a curve. We will imagine a curve that starts at t equals a and ends at t equals b. The challenge is that the distance formula only gives us the length of straight line paths, so we will approximate the curve with a bunch of straight line segments, and then take the limit as we increase the number of segments. We're going to use a differential notation because it's more intuitive than the full formulas as written in the book. Let's imagine taking a close look at just one of these straight line segments. Even though in the initial sketch it's in 2 dimensions, we're going to think of it as being in 3 dimensions. So if we plot the endpoints of this particular line segment, it fits inside a box with sides that we'll label dx, dy, and dz. By applying the distance formula, we know the length of this segment, which we'll call dl, is equal to the square root of dx squared plus dy squared plus dz squared. You should think of dl as a little bit of length. Then the total arc length is the sum of these lengths. If we look at the right side of the equation, we don't have a variable of integration. We also need to convert the differential terms into derivatives. Fortunately, the parameter t saves us on both counts. We can factor out a dt from under the square root, which leaves us with derivative terms underneath and a dt on the outside. And this is the arc length formula. Notice that the square root part is actually just the length of the derivative vector. This gives us a more compact formula for arc length. The limits of the integral are the values of t that mark the starting point and the ending point of the curve. One of the challenges that we've seen with parameterizations is that there are multiple parameterizations of every curve. We can change where we put the 0, and we can traverse the path at any speed we want. This flexibility makes it difficult because there's no standardization for how we view the curve. The arc length parameter changes all of that. Rather than using an arbitrary value to parameterize a curve, we're going to use the physical distance. Once we establish the location of 0, then all the points are measured by their distance along that path. You can imagine taking a piece of inelastic string that we label with distances, and then lining up the string along the curve. The markings on the string correspond to the values of the arc length parameter along the curve. We can also follow this backwards to get negative values. Another way to think about this is that these points are mile markers along the side of a highway. Every unit distance, the marker goes up by 1. To get the arc length parameter, we have to define the arc length function. Let's say we have a parameterized curve r of t defined on the interval from a to b. The arc length function s of t is defined to be the length of the curve from a to t, where t is some point in the interval from a to b. Since we have the arc length formula, we can just write that down. The variable s is called the arc length parameter. Notice that we're using the variable w because the variables s and t have already been used up. S is the arc length parameter, and t is the upper limit of the integral. That's how things go sometimes. We just need to make sure that we're not using a symbol that has already been used for something else. As long as t travels the path without ever stopping or going backwards, we will get a function that's invertible. If we're able to invert this function, Then we would get t as a function of s, which we can then substitute to get the curve parameterized by the arc length parameter. Those last steps are often confusing in the abstract, so we will outline a computational process and do a quick example. The goal is to parameterize a curve by its arc length given some parameterization using a generic variable t. The first step is to calculate the arc length function. This will give you an equation of the form s equals something in terms of t. The next step is to solve for t from this function so that you end up with the equation of the form t equals something in terms of s. The last step is to just plug this into the original formulas so that your curve is parameterized with the variable s. These are the steps that we're going to follow in the upcoming example. Let's take a look at the curve r of t is equal to 5 cosine t, 5 sine t, where t runs from 0 to 2 pi. You should be able to immediately recognize this as a circle of radius 5, but even if you don't, you should be able to do the calculation anyway. We simply plug this into the equation for the arc length function. Notice that even though this is a two-dimensional vector, the ideas still apply. We won't talk through the details of this integration, because this is an integral that you should have seen many times by now, and you should be able to recognize the trick of using the Pythagorean identity to simplify the radical term. This gives us the equation s equals 5t. The next step is to solve for t. It's easy in this example, but this can often be a very challenging step. And then we substitute this in for the t that's in the original vector equation, making sure that we also adjust the interval. And this gives us the curve parameterized by the arc length parameter. You may have noticed that the arc length parameter makes the equation look a bit messier. On the plus side, the arc length parameter has the property that the derivative of the position vector is always a vector of length 1. This corresponds to the idea that you're traveling at a constant speed of 1 unit of distance per unit time. The book also works through a more complicated example in which you have to work a little bit harder to get the inverse. You should take the time to work through that one on your own. In the next video, we're going to talk about the geometric concept of curvature. The curvature of a curve is a way to measure how fast the curve is bending at any given point. A straight line has zero curvature since it doesn't curve at all, and a very sharp bend has a very large curvature. The intuitive idea is that we're measuring how quickly we're changing direction as we travel along the curve. The tangent vector gives us the direction we're facing, and we can look at the change of the direction of the tangent at two different times to get a sense of how fast we're changing direction. But this starts to introduce some problems for us. If you think about a roller coaster, it's not hard to understand that the rate at which the direction changes depends on how fast you're going. And how fast you're going is related to the parameterization that you've used. We want the curvature to be related to the curve itself and not an arbitrary parameterization, which is where the arc length parameter comes in. The arc length parameter is defined by the shape of the curve and gives us the parameterization if we're moving along the curve at a constant unit speed. We're going to introduce a new idea known as the unit tangent vector. This is the vector that is parallel to the tangent vector that has length 1. We get this by dividing the tangent vector by its length. Remember that vectors are objects with both a direction and a magnitude. If we fix the magnitude to be 1, then the information in the vector is really just the direction. In fact, these vectors are sometimes referred to as direction vectors because of this. In the previous section, we noted that when the position is parameterized by the arc length parameter, the derivative has length 1. This means that under that parameterization, the derivative of position gives us the unit tangent vector. Since there is no forward or backwards acceleration as we move at a constant speed, all of the acceleration goes into changing our direction, and the curvature is the measure of how large that acceleration is. Since the derivative of velocity is acceleration, we are interested in the magnitude of that vector, and that takes us to the formal definition. Definition: if C is a smooth space curve, and S is an arc length parameter for C, then the curvature of C is the length of the derivative of the unit tangent vector with respect to S. The fancy-looking K is the Greek letter kappa. The more formal way to arrive at this formula is by working directly with the rate of change of the direction. The book does this derivation, and you should go read that part of the section to get the full treatment. This formula is great, except that it requires us to have the arc length parameterization, and we've seen that the arc length parameterization is sometimes difficult to calculate. If we have a general parameterization, then we need to do more work. There are two other formulas that you can use for the curvature when you only have a general parameterization. The first one is derived by applying the chain rule, and it's just straightforward algebra and calculus. The second one uses a more vector-based approach. There is a purely geometric interpretation of the curvature that's worth considering. We know that we can approximate curves near a point using the tangent line. But those aren't the only approximations we can use. It turns out that a curve can be approximated near a point by using a circle. We might even view this as a better approximation than a straight line, because we can mimic the curviness that exists at that point. There's a circle known as the osculating circle that is the best circle to use at a point to approximate the curve. The roundness of the curve and the osculating circle perfectly match one another at the point of tangency. Curvature is the reciprocal of the radius of the osculating circle. The circle will have the property that at the point of tangency it shares the same slope and also has the same curvature. Arc length and curvature both have numerous applications. For example, on a roller coaster, knowing the curvature of a turn will allow you to calculate the acceleration that will be experienced at any specific speed, which tells you how fast the ride can go without injuring the riders or damaging the equipment. Unfortunately, those things are beyond the scope of this course, so we'll have to set them aside, but hopefully the idea of it will motivate you to look into this a little bit more for yourself. As we continue in our study of multivariable calculus, we're going to once again remind you that even though we're mostly working with just 2 independent variables, most of the ideas that we develop can easily be extended to 3 or more independent variables. When we took derivatives of vector-valued functions, we were taking the limit of a function of a single independent variable. Because it was a function of a single variable, we didn't really need any new calculus ideas because it still came down to the same derivative formula. So although we have been working in multiple dimensions, we have not done anything new with the derivative. But now we want to look at derivatives of functions of 2 independent variables. While the core concepts are going to be similar, we're going to need to expand our definitions. The first definition we'll expand is our concept of a limit. Definition. Given a function f of the independent variables x and y, we say that f has a limit L as xy approaches ab, provided that we can make f of xy as close to L as we like by taking xy sufficiently close but not equal to the point AB. And this is the notation that we use. Since you've already taken single variable calculus, these ideas should be familiar. You may have even encountered the formal epsilon delta definition of a limit in your previous calculus courses. You can use the same formulation for this, but the book sweeps that notation under the rug, and we will as well. The idea of being close but not equal to should remind you of graphs with removable singularities, where the function looks like it's headed towards one value, but when you get there, the value is something else. Remember that this function still has a limit because we're looking at points that are close to but not equal to the destination. When the limit and the value match up, we say the function is continuous, and that's something we'll loop back to shortly. In single variable calculus, there are only 2 sides that you can approach the limit from. You're either approaching from above or below. But for a function of 2 variables, you can approach the limit from all sorts of directions. Furthermore, you don't even have to approach from a straight line. The limit must be the same every single way that you want to approach the point. The power of the limit concept is that it is so stringent. This makes it somewhat easy for us to show that limits do not exist. All we need to do is identify 2 paths towards the same point that evaluate to different limits. In practice, you would need to write down some sort of function that defines a path towards the limit and then substitute. Activity 10.1.2 uses the function f of xy equals x over the square root of x squared plus y squared, and asks you to consider the limit at 0, 0 using straight lines of the form y equals mx. The key fact is that for this function, as x goes to 0, so does y. This means that you can make the substitution and calculate the limit along that line. In this calculation, the final result ends up not being a constant, but a value that depends on the slope that you picked. And this means that different ways of approaching 0, 0 can lead to different values, which means that the limit does not exist. Proving that a limit does exist turns out to be much more difficult. The problem is that you cannot use a path-based approach. There are infinitely many different paths you can take, and there's no single collection of formulas that accounts for them all. The book does an example of this that you should work through. Although the skills that are developed won't be used anywhere else in this course, the basic skills of working with inequalities and logic that are used really ought to be in your toolbox. The book lists 5 properties of limits. and while there's a lot of notation here, the ideas are simple and should be familiar. As long as the limits of our functions exist, then there are certain properties that they follow. The first one states that the limits of isolated variables are exactly what you think they should be. The second is that constants can be factored out of the limit. The third and fourth show that the limit respects addition, subtraction, and multiplication. The fifth one says the same with division, as long as you do not end up with division by 0. These results are important because it justifies all of the algebraic manipulations we're going to perform, but in practice, these end up being exactly the manipulations that you've been trained to do throughout your mathematical experiences, and so it's not that informative. The main consequence of these properties is that for the nice functions that we're working with, everything works out the way we expect they would. Earlier, we brought up the idea of continuity. A function f of a single variable is continuous at a if it satisfies three properties. F of a exists, the limit of f as x approaches a exists, and these two values are the same. Looking back at the removable singularity from earlier, we see that it isn't continuous because it fails at the third property. The limit approaching x equals a is not the same value as the function at x equals a. Continuity for multivariable functions is defined in the same way. Definition: a function f is continuous at the point ab, provided that f is defined at ab, the limit of f as xy approaches ab exists, and the two values are the same. The book goes on to list a number of continuity properties, which are basically just reflections of the four limit properties from earlier. In short, continuous functions behave well with respect to addition, subtraction, multiplication, and division, as long as you're not dividing by 0. In our applications, the functions we're working with are basically all continuous. Our points of potential discontinuity are primarily from points that lead to division by 0. These technical conversations are important at higher levels of mathematics, but for this level it would be overkill. The functions that we're going to be working with are nice functions, and we don't have to worry too much about the pathologies. Recall that the trace of a function is the function we get when we fix one of the two input variables. When we look at the graph of a trace, we get something that ends up being a single variable function. And since it's a single variable function, we can apply our single variable calculus concepts to it. Specifically, it makes sense for us to ask about the slope of a function along a trace. And that idea is exactly what the partial derivative is. Definition: the first order partial derivatives of f with respect to x and y at the point ab are given by these formulas, provided that the limits exist. This notation can seem like a lot, but if you break it down, there's not really that much to it. Let's look at the partial derivative with respect to x. The first thing to notice is that this is a difference quotient. It's the evaluation of a function at two locations divided by the distance between those two locations. Here's what it looks like on the xy plane. We are evaluating the function at the points ab and a plus hb. The point ab is in one position, and a plus hb is to the right of it, a distance h away. If we look at what's happening on the y equals b plane, we get a piece of the curve, and the difference quotient is the slope of the secant line. And then we're taking the limit as h goes to 0 to get a derivative. This is called the partial derivative with respect to x, because we're only looking at how the function changes when moving in the x direction. The partial derivative with respect to y is the same idea, except now we're asking how the function changes if we only look at what's happening in the y direction, and that is the heart of what partial derivatives are. There are two notations for the partial derivative. We have presented things with the subscript notation. Notice that we cannot just use a prime to denote the partial derivative, because it doesn't indicate which derivative we're taking. Another notation for partial derivatives is known as the Leibniz notation, which is the notation that uses fractions. It's written with this fancy-looking d rather than a normal d to indicate that it's a partial derivative. We will never use the regular d for a partial derivative. When it comes to calculating partial derivatives, the key fact to remember is that you're treating one of the variables as if it were a constant. That comes from the fact that on the graphs of traces, we're fixing one of the variables to be a constant. This means that if we take the partial derivative of x squared y cubed with respect to x, we can factor out the y cubed part and just focus on the x squared part. Students sometimes make mistakes with the chain rule, especially when working with exponential functions. For the first few times you do these calculations, I recommend you take your time and write out the derivative with the chain rule step explicitly to help avoid errors. The first order partial derivatives are measures of the slope of a surface if you restrict yourself to moving in either the x or the y direction. If the slope for one of the variables is positive, then increasing in that variable causes the function to increase, and decreasing in that variable causes the function to decrease. If the slope is negative, then this is the opposite way around. And if the slope is 0, then there's no change. The nice part about this is that it fits perfectly with your previous knowledge about slopes. A more interesting question is what happens when you move in some arbitrary direction. At this time, we don't have any information about that situation, but it's worth trying to imagine how it might work. This is an idea that we're going to pursue later in this chapter. Sometimes you aren't given a formula for a function, which means you won't be able to use your calculus formulas to calculate the derivative. Instead, you may need to make estimates based on the given information. The two situations we're going to consider are when the function is described by a chart and when the function is described through contour lines. This is table 10.2.7 from the book. It is a chart of the wind chill in Fahrenheit as a function of wind speed and temperature. Let's suppose the wind speed is 15 miles per hour and the temperature is negative 10 degrees. Based on this chart, the wind chill is negative 32 degrees, which means that even though the air temperature is negative 10 degrees, it feels like it's negative 32 degrees. If we wanted to estimate the partial derivative with respect to v, we are asking how the wind chill changes as we increase the wind speed. If you look at the chart, we see that the next wind speed we have is 20 miles per hour, which is 5 miles per hour faster. In that span of 5 miles per hour, the wind chill drops by 3 degrees. So the temperature drops 3 degrees for every 5 miles per hour of increased wind speed. We can translate this into an estimate of the partial derivative. The partial derivative is negative 3/5 degree per mile per hour. This value is the slope of the line that passes through the 2 points on the graph. And that is the basic intuition of what it means to be a partial derivative. How much does the function change if you change one of the input variables by a small amount? Remember that this is not an exact derivative, since we're not actually taking a limit. We're just making an estimate. It's worth pointing out that there are multiple ways to estimate the slope. The process we just completed is known as a forward difference, and it's called that because we're using a forward step to estimate the slope. Another approach would be to use a backward difference. Notice that these two approaches will usually give different values. You can also do a central difference, which is when you use both a forward step and a backward step to estimate the slope. This approach takes more information into account and will usually give a better estimate of the slope. If you are working with a contour plot, the idea is the same, but you're going to have to work harder to get the values of the function. Here's the plot from the book. If you wanted to evaluate the function at 0, 0, you will need to observe that this point is between the contour lines of heights 3 and 4. You won't get an exact answer, but if you look at the location, you can see that it's a little closer to the 4 contour than the 3 contour. And so maybe this is about 3.7. This is a rough estimate, and that's just the nature of the problem. If you wanted to estimate the partial derivative with respect to y, you need to estimate the function at another point above or below it. You can know that the function is exactly 4 by going down to the contour line, but then you're going to have to estimate the coordinate. The same thing happens if you go up to where the function is equal to 3. Or you can move a distance of exactly 1 in either the positive or the negative direction, but then you're going to have to estimate the value of the function. There's no real way around the estimation, but whatever estimate you choose, to approximate the partial derivative, you need to set up a difference quotient. Partial derivatives are a key tool for the remainder of the course. Please take the time to practice the computational aspects of it and think through the conceptual aspects of it to make sure that everything makes sense to you. The derivative of a function is itself a function, which means that we could take the derivative again. In single variable calculus, there's only one type of derivative, so it makes sense for us to say the second derivative. But as we saw in the previous section, if you have a function of 2 variables, then you have 2 first-order partial derivatives. If we were to take another derivative, we would again have 2 choices. This means that there are 4 second-order partial derivatives. When looking at the notation for higher order partial derivatives, it's important to understand the meaning of the symbols. You will notice that the two notations have the orders of the letters swapped for the same thing in the cross derivatives. The key to keeping this straight is to think about how parentheses would imply the order of operations. If you put parentheses around the subscript notation, you'll find there's only one reasonable way to do it. With Leibniz notation, the numerator takes some getting used to, but you can look at the denominator and think about parentheses to understand the order. The nice part about all of this is that if you know how to take first derivatives, you know how to take second derivatives. Just make sure to keep track of which variables are constant at each step. An even nicer fact is that for the functions that we will be working with, the mixed derivatives will always be the same no matter what order you calculate them. This result is known as Clairaut's theorem. The key technicality is that you need the mixed partial derivatives to be continuous near the point where you're taking the derivative. For all the functions we're working with in this class, that will always be true. However, there are examples where this condition is not met, and it's important to keep that in the back of your mind when working with mixed partial derivatives. Recall that in single variable calculus, the second derivative gave concavity. If the second derivative is positive, the curve is concave up. If the second derivative is negative, it's concave down. And if the second derivative is 0, then we don't know what the shape is going to look like. The second order partial derivatives xx and yy follow the same concept. This makes sense because both partial derivatives keep the same variable fixed, and so you're constrained to movement on a single plane. But the mixed partial derivatives are a bit more complicated. It turns out that the mixed partial derivatives give a measure of the twistiness of the graph. That's not a technical term, but it does convey the appropriate intuition. Let's take a closer look at it. Let's think about what f sub x sub y means. The inner derivative is the partial derivative with respect to x. In other words, it's the slope of f in the x direction. We are looking at the partial y derivative of this value, which is telling us how the slope is changing when we change the value of y. This can be difficult to visualize. We're going to imagine a sequence of traces in the x direction. We've sketched some planes in 3 dimensions to help you visualize what this looks like, and we're going to line up those traces on top of each other. We're going to fix a specific value of x, say x equals a, and draw the slopes of each of the traces at that point. If we align these slopes with each other, we can start to get a visualization of the slope changing as y increases. If you imagine the slope being like a surface that you're riding on, you can see that it's twisting a bit to the right as time moves forward. That's the idea we meant by twistiness earlier. In this case, the slope is decreasing as we move forward, so f sub xy is less than 0. And the larger the value is, the faster we're twisting. This is a quick visualization of the second derivative. We'll leave it as an interesting mental exercise to think about what's happening in the other direction with f sub yx, and in particular why these two values are the same if things are nice and continuous. These pictures tend to be easier for people who are more visual than those who are less visual, and that's okay. It's the practice of learning to think carefully about the meaning of these pictures that matters, not that you can do it quickly or that it's intuitive. As you continue along in mathematics, you will want to focus on the practice of thinking carefully much more than you will want to focus on thinking quickly. This is counterintuitive for a lot of students, as they tend to think that better and faster mean the same thing. That's just not how it is. You want to move towards the idea that clearer and more precise thinking is better, because that's the skill that will sustain you when things get more difficult. The book starts this section with a technical note about linear approximations. In the last chapter, we talked about approximating single variable functions with lines, but we didn't look at any of the details of it. It turns out that this only makes sense if the function itself looks like a line near our approximation. A classic example of a function that isn't locally linear is the absolute value function at x equals 0. No matter how much you zoom in, you will never eliminate the corner, and so it will never look like a line. There is a similar condition for functions of 2 variables. We say that a function is locally linear near a point if the graph looks like a plane near that point. And there are examples similar to the absolute value function that fail to be locally linear functions of 2 variables. The book goes on to discuss some theorems about when functions are locally linear. There's a theorem that says that for single variable functions, if the derivative of a function exists at a point, then the function is locally linear at that point. But the theorem does not extend to multivariable calculus. Knowing that the partial derivatives exist at a point turns out to be insufficient to know that the function is locally linear. And you don't even need to come up with a crazy example. The function x to the 1/3 y to the 1/3 has both partial derivatives existing at 0, but the function is not locally linear there. The purpose of all of this is to remind you that there's another level of ideas and complexity to calculus that goes beyond just the computations. We're only scratching the surface of some of these high-level concepts. The work that we're going to do uses the following theorem. Theorem: if f of xy has continuous first-order partial derivatives, then the equation of the plane tangent to the graph of f at the point x0, y0, f of x0, y0 is this equation. When the function is locally linear, this tangent plane can be used to approximate the function near the point x0, y0. We can also turn this around. If we are given the tangent plane of f at x0, y0, then we can use this to read off the values of the partial derivatives of f at x0, y0. It doesn't even need to be in exactly the tangent plane form, as the partial derivatives are the coefficients of x and y. The other terms are just constants that have been rearranged and simplified. Students sometimes get confused by this because they try to match up the equations too literally. The manipulations to undo the step of combining the constants is not hard, but it's also not that important, so we're not going to elaborate on it. Linearization is an important calculus concept. It's part of a larger topic of finding different ways to approximate complicated functions by using simpler functions. You might remember learning about Taylor series expansions in single variable calculus, which allows us to approximate functions using only polynomials. Linearization is a simple example of this. If we graph a smooth curve and its linearization and then zoom in close to the point of tangency, we can see that there's only a small difference between the curve and the tangent line. We want to mimic this idea, but using a surface and the tangent plane. Remember that the goal is to get a good approximation of the function. It's important to compare the formula for the tangent line and the tangent plane because there are a number of important parallels. Notice that they both evaluate the function at the tangent point. This term plays the role of anchoring the approximation of the function. Then we have a derivative term multiplied by a difference term. We also see that the derivative term is evaluated at the point of tangency, and that the variable of the derivative corresponds to the variable in the difference. The derivative term gives us the slope of the function in a specific direction, and the whole term can be thought of as a change of the function due to moving in that particular direction. Although we won't do it here, we can expand this idea and use the second order derivatives to get a better approximation for the function, just as we can use higher order derivatives to get more terms in the single variable Taylor series. This gets more complicated because we have many types of the higher order derivatives, but it's not so complicated that you won't be able to understand the basics of it on your own with just a little bit of thinking. In the next video, we're going to take a look at differentials. We used differential notation briefly when we were working with arc length. This is when we used dx, dy, and dz to represent a little bit of movement in the x, y, and z directions, and then used dl to represent a little bit of arc length. This differential notation has some other applications that we're going to look at here. Given a function f of xy, we can use the tangent plane near the point x0, y0 to get an approximation of its value at nearby points. While we can use a generic xy to denote a nearby point, we want to pick a notation that emphasizes the nearness. So we're going to call the nearby point x0 plus dx, y0 plus dy, where we implicitly view dx and dy to be small values that represent the shift in the x and y directions. When we look at the linearization, we see that it can be broken up into two pieces. The base value is f of x0, y0, and the rest of it is the change, which we call df. When we move the point by a small amount, the function f changes by a small amount from its baseline value. We can also see that if we substitute for x and y using the dx and dy relationships, that the difference terms simplify. Putting it all together, we get df equals this quantity. In Leibniz notation, this is written as df equals partial f partial x dx plus partial f partial y dy. Remember that since we're using a linearization, we're making an approximation of the change of f and not the true change of f. For the true change of f, we would use delta f. This is a subtlety that we don't need to dwell on here, but just remember that differential notation is implying that we're using an approximation of some type in the calculation. Let's look at an example. Suppose you have a machine that cuts rectangles. It's supposed to cut rectangles of width 20 centimeters and height 10 centimeters. However, because of machining tolerances, the width can be off by as much as 0.2 centimeters, and the height can be off by as much as 0.4 centimeters. We are going to use differentials to approximate the potential error in the area. In the sketch, we've shown dx and dy to be positive values, but they could just as well be negative values. The shaded area is just a representation of the possible error, which we're going to approximate using differentials. The formula for area is A equals xy, where x is the width and y is the height. We will first calculate the derivatives. Then, by using the differential, we can compute the error estimate dA equals y dx plus x dy. We can then substitute in our values to get that dA equals 10, which shows that the area can be off by as much as 10 square centimeters. As a student, this sort of problem always confused me. Why not just use the area formula and get the exact maximum error? Why even bother with differentials? In practice, you don't always have a formula. This means that the calculation of the derivatives is often the result of a numerical estimate and not an analytic derivation. And so in more practical settings, you simply don't have access to those things. Specific to this problem, we can absolutely get a more precise answer. But that's just not the exercise we're being asked to do. Problems like this, where you have an exact formula from the beginning, are really just an artificial construct to provide an opportunity to practice multiple skills. The first skill is just practicing how to read and interpret word problems. Then there's the ability to calculate the partial derivatives correctly, and the last skill is to understand the use of differentials and linearization to estimate the change of a function. So don't be like me and don't overthink it. The main ideas here are that you can use the linearization to estimate the change of a function if you change the inputs by a small amount, and that this can be represented using differential notation. In single variable calculus, the chain rule is the formula that we use to calculate the derivative of a function when you have one function inside of another one. An example of such a function is sin of x squared. Most students remember this as there being an inside function and an outside function, and the calculation of this should be basically automatic. But as a reminder, this is technically a composition of functions. If f of x equals sin of x and g of x equals x squared, then f of g of x is sine of x squared. And applying the chain rule formula directly is how we get the result. The idea of the chain rule is that you're trying to figure out how the function f changes as the variable x changes, but there's a function that's changing in between them. The variable x changes the function g, and the changes of g impact how f changes. In the previous section, we saw how the changes of a two-variable function depend on what's happening in the x direction and in the y direction, and the changes in each direction may be different. So we need to incorporate all of that information into our formula. Let's be a bit more specific. Imagine a person hiking along a trail, and let's think about how we might model their elevation above sea level over time. If we imagine looking down from the sky, the trail creates a path that can be modeled in the xy plane. The hiker's position would then be a function of time, and we can denote the time axis as a horizontal line. At any moment of time, the hiker is somewhere along the trail. This creates a function from the variable t into the xy plane. Furthermore, at any given location, the trail is at a certain elevation. This creates a function from the xy plane to the variable z, which we'll put off to the side. As the hiker moves along the trail, their elevation goes up and down along that axis. This is a composition of functions. At any given time, the hiker is in some location. At any location, there is an elevation. So at any given time, the hiker is at some elevation. If we pick multiple time values, we get multiple elevations, and this gives us the outline of the graph of elevation at any given time. Now let's think about how the elevation changes with time. Clearly, if the hiker is moving faster, the elevation is changing faster. But the change of elevation also depends on the shape of the path. Running up a steep slope will lead to a faster change of elevation than walking along a gentle grade. So the change of elevation with respect to time needs to incorporate both elements. Here's the formula for the chain rule. Let's try to understand the individual pieces. On the left we have the derivative dz dt. This is the rate of change of the hiker's elevation with respect to time. On the right we have two terms. The first term is the change of elevation due to motion in the x direction, and the second term is a change of elevation due to motion in the y direction. The partial derivative terms give us the slopes of the terrain in each direction, and the time derivative terms are speeds. It's the combination of slope and how fast you're moving that gives the change in elevation. And that's the basic intuition of the chain rule. We're breaking up the change of the function z into changes that can be attributed to movement in the x direction and the y direction. The chain rule can feel confusing because there are often 4 or more variables in the problem at the same time, and so it is helpful to have a scheme to organize that information in a helpful way. The section on tree diagrams is supposed to help with that. The core idea is that we're keeping track of the relationships between variables. A tree is a type of mathematical graph that can be used to represent those relationships. At the top of the tree, we have the outermost function, and as we work our way down the tree, we're keeping track of the internal dependencies. Here's a tree diagram for the function we were just working with. Notice that z is at the top, and that z is a function of x and y. This is the statement that our altitude depends on our location. But we can see that x and y are functions of t. This is the statement that our position depends on what time it is. So as we read down the tree, the branches show us the variable dependencies. Each of the connecting bars represents a derivative. It's the derivative of the top variable with respect to the bottom variable. You have to decide whether it's a regular derivative or a partial derivative, and that simply depends on whether the top function has one or more branches sticking out of it. So the top left branch is partial z partial x. The top right branch is partial z partial y. The two bottom branches are the regular derivatives dx dt and dy dt, since the variables x and y only have one variable of dependency. To construct the derivative dz dt, we simply find all the places where t is at the bottom of the tree, multiply all the derivatives along connections going back up to the top, and then add the results together. We can see that there's a left path and a right path. On the left path, we have partial z partial x multiplied by dx dt. On the right path, we have partial z partial y multiplied by dy dt. This is a situation where a simpler example feels more complicated because it's hard to see what's actually happening. So we're going to look at a more complex situation. Here's another tree diagram. In this case, the function w depends on 3 variables x, y, and z. And each of these depends on the variables s and t. This means that we can view w as a function of the 2 variables s and t. How can we calculate the partial derivative of w with respect to s? We'll start by identifying all of the places where s is at the bottom of the diagram. This gives us a number of branches to trace up to the top. For each of these branches, we write down the corresponding derivatives. We then multiply the derivatives that are along the same paths and then add the results. The same idea would hold if we had another layer of dependency, and this gives us a strong hint as to the value of organizing the information in this way. Imagine if you had to simply memorize a bunch of different formulas to account for all the different relationships between the variables. It would be very difficult. One of the key ideas as you get further along in math is to understand patterns and relationships more deeply. This helps us to make connections between ideas and allows us to gain a deeper understanding of and appreciation for the concepts that we're working with. As we continue moving forward in this class, I hope that you will make some time to think beyond what's immediately in front of you and try to relate what you're studying to things you've seen previously in your mathematical experiences. This will really help you grow as a student of mathematics, and it's a practice that will help you in the long run. So far, we've looked at the partial derivatives to tell us the slope of a function in the x and y directions. But there are lots of other directions besides horizontal and vertical. So we are going to develop the concept of a directional derivative, which is the slope of a function in any direction. When we took the partial derivatives, we were using a step size of h in either the positive x or y direction, and then let h go to 0. We're going to do the same thing, except free ourselves up to move in any direction. If u is a unit vector that we write as u1, u2, then we can multiply it by h to get a vector of length h. And this vector shows us the change in x and y if we take a step of size h in the direction of u. Then the directional derivative is just the limit of the difference quotient as h goes to 0. Definition. Let f of xy be a function. The derivative of f at the point xy in the direction of the unit vector u is denoted as d sub u of f of xy, and is given by this formula for those values of x and y for which the limit exists. D sub u of f of xy is called a directional derivative. This gives us the slope of a function when moving in the direction of u. There's not too much to say about this formula, as it's just a difference quotient using a step size h in the direction of u. One important element to remember is that u needs to be a unit vector for this formula to be correct. This formula is a little more difficult to work with because we are changing both variables at the same time, so we're going to take a more careful look at it. Suppose we have a function f, and let's fix a specific point x0, y0 and a specific vector u1, u2. To get the directional derivative, we're going to focus on the line that passes through the point x0, y0 whose direction vector is u1, u2. Here's the parametric form of that line. Notice that we now have a situation where we can apply the chain rule. The function f depends on both x and y, and both x and y depend on t. Furthermore, the derivatives of x and y with respect to t just give us the constants u1 and u2, and this means we have a formula for df dt. It turns out that u being a unit vector means that we are moving along the line at unit speed, and this corresponds exactly to the directional derivative. The justification for this can be done algebraically, but it's more intuitive to observe that this concept of unit speed is what we use for partial derivatives in the x and y directions, and so this is the natural way to generalize it. Again, it's important that we are using a unit vector in this formula. If you're working on a problem where you aren't given a unit vector as the direction vector, you're going to have to divide it by its length to turn it into a unit vector before doing the calculation, otherwise you'll get it wrong. If you look at the formula for the directional derivative, you might pick up on the fact that it looks like a dot product. Specifically, it's the dot product of the vector of partial derivatives with the vector u. This vector of partial derivatives turns out to be an important and useful value in calculus, so we give it a special name. This is known as the gradient of f, and it is written with this upside down triangle. The symbol is called a nabla, but it's often just called del. So the gradient of f, or del f, evaluated at the point x0, y0, is the vector of partial derivatives evaluated at the point x0, y0. Notice that we've put a vector symbol over the del. As always, this implies the result is going to be a vector, but there's more to it. The del notation is sometimes treated like an operator, so del is the vector of partial derivative operators. This is a handy notation because it means you can now imply formulas using vector operations. For example, if you have the vector function f equals f1, f2, we can write del dot f and come up with a meaningful interpretation of what this calculation is supposed to be. This is actually known as the divergence, and it's a concept that's important when working with vector fields, which is a topic that's sometimes covered in multivariable calculus, especially if you're on a physics or engineering track. The del operator generalizes to 3 or more dimensions in the way you might expect it to. If our independent variables are x, y, and z, then del is the operator where the partial derivatives are with respect to x, y, and z. We're not going to go into all the details and nuances of this notation, but if you go on in mathematics, operators become part of the language you use to describe math, and you will become more acquainted with the ideas at that point. In the previous video, we introduced the gradient of a function and its notation, but we didn't talk about what it actually represents. Since the gradient of a function is a vector, we know that it is a quantity that has both a magnitude and a direction. We're going to start by looking at its direction. We arrived at our formula for the directional derivative by thinking about the algebraic formulation of the dot product. But since we're trying to understand the geometry of the gradient, it makes sense for us to think about this dot product using a geometric formula. Remember that u is a unit vector, so its length is 1. The angle theta is the angle between the gradient and the unit vector. By substituting this information into the geometric formula for the dot product, we get this result. We are going to think through the case where the gradient is perpendicular to u. There are a lot of little steps in the logic, so you may need to watch this a couple times and pause it to make sure you really understand the steps. If theta is pi over 2, then the dot product is 0. That dot product represents the directional derivative, so the directional derivative is 0. The directional derivative tells us the slope of f in the direction of u, and since the slope is 0, the function is not changing in that direction. If we move along a path where f is constant, we are moving along a level curve of f, and so u must be tangent to the level curve of f at that point. But since u is perpendicular to the gradient of f, we know that the gradient of f is perpendicular to the level curve at that point. In fact, we can push this even further. Now let's suppose that u and the gradient point in the same direction. Then theta is equal to 0, and the cosine function is at its maximal value. And this means that the dot product is at its maximal value, so the directional derivative is at its maximal value. Another way of saying this is that when u is parallel to the gradient, the directional derivative is as large as possible. This means that the gradient is pointing in the direction that gives us the steepest positive slope. If u and the gradient are pointing in opposite directions, then the dot product is at its smallest value, and this means that the direction opposite the gradient is the direction of steepest descent. Again, the logic here requires a lot of little pieces coming together, and so it's going to feel like it went quickly. This is a situation where you need to set aside some time and think through each step to make sure you understand it. This is the sort of mental exercise that really helps you to become a more careful thinker if you do it, and that skill pays off in ways that go well beyond this class. The book talks about applications of the gradient using the context of simulating heat-seeking missiles by measuring the local heat gradient. You're encouraged to read about that in the book. I'm going to use a couple different ideas. Let's think about the consequences of the gradient pointing in the direction of steepest descent. What this means is that if we imagine the function as a surface and place the ball somewhere along it, the ball will naturally roll downhill in the direction opposite the gradient. And this idea can be used as a basis for modeling how water would run down the side of a hill. And that's one application of the concept of the gradient. Another application comes from the world of data science. A common task in mathematical modeling is finding the equation of a line that is the best fit for a bunch of points. Usually these points aren't in a perfect line, which means that any line that we draw is going to have some error associated with it. Intuitively, some lines will have larger errors than others. The goal is to find the line that minimizes the error. In other words, the error is a multivariable function and we're trying to minimize it. This is often an extremely complicated function, so that we don't have a good analytical formula to use our normal optimization techniques from calculus. And so we need a different tool. That tool is known as gradient descent, and it works in a similar way as the ball rolling downhill example. We can try to find our way to the minimum value by estimating the negative gradient of the function relative to our current input values, and use that to give us a new set of parameters. And by repeating this, we can hope to converge to the values that give us the smallest error. So far, we've talked about the direction of the gradient, but what about its length? There's not nearly as much to say about this, but we also can't ignore it. Let's return to the directional derivative equation we were analyzing earlier. When u is parallel to the gradient, theta is equal to 0, and this expression simplifies to just the length of the gradient. We have already seen that the gradient points in the direction of steepest ascent. But with this additional observation, it means that the length of the gradient is the slope in that direction. In other words, the length of the gradient gives the maximum rate of change of the function from that location. And this is another way to interpret the meaning of the geometric properties of the gradient. The gradient of a function and the del operator are important tools for multivariable calculus. We're going to see a number of different applications of it over the next couple sections. In single variable calculus, we had the first and second derivative tests to help us find the maximum and minimum of a function on an interval. You may also remember that we had to check the endpoints of the interval if the interval was finite. All of these have analogous multivariable concepts. We'll start with some formal definitions. Note that I wanted to make the third and fourth definitions to use parallel language, so I adjusted the wordage slightly from the book's presentation. I'm not going to read these definitions in full because the concepts should be familiar. These ideas are all essentially the same as from single variable calculus. A local minimum is a point on the graph that is lower than all the nearby points. A local maximum is a point on the graph that is higher than all the nearby points. The absolute minimum or maximum are points on the graph that are less than or greater than all the points on the entire graph. The picture in multivariable calculus is a little more complex because the nearby points are now in infinitely many directions instead of just to the left and to the right, but the basic ideas are unchanged. Critical points for single variable calculus occur where the first derivative of the function is equal to 0 or is undefined. When working with multivariable functions, we have multiple first derivatives to worry about. The key fact is that to be a critical point, they must all be 0 at the same point. Definition: a critical point of a function f is a point in the domain of f for which the partial x and partial y derivatives are both equal to 0 at that point, or where at least one of the two partial derivatives fails to exist. Notice that both equations need to be 0 at the same time. This can sometimes lead to situations where you need to solve a simultaneous system of equations. For the problems we'll encounter, these may not be linear equations, but they will be equations that can usually be solved by some type of substitution or elimination or possibly factoring. Students often forget about the possibility of a derivative not existing as a critical point. Fortunately, this usually arises out of something like division by 0, where it is clear that extra attention is required, so keep an eye out for that. Identifying critical points is the first step to identifying the extreme values of a function. But we also need to use a second derivative test. Functions of two variables are more complicated than functions of one variable, as there are 4 second derivatives, though 2 of those are usually the same for us by Clairaut's theorem. For single variable calculus, we had the concept of concavity. If the graph is concave up, the critical point is a minimum. If the graph is concave down, then the critical point is a maximum. We then have the case where the second derivative is 0, which could be a minimum, a maximum, or neither. For multivariable functions, there are more shapes. We still have something that looks like concave up and concave down, but we have to add the possibility of a saddle point, which is neither a minimum nor a maximum. But it's not quite like having the second derivative equal to 0. In that case, the second derivative test tells us nothing. But a saddle point is definitely neither a minimum nor a maximum. This is called a saddle point because it's basically the shape of a saddle like what you would use with a horse. When you sit in a saddle, it's concave up from front to back to keep you in the middle, but it's concave down from left to right so that your legs can go down around the sides of the horse. This mixture of being concave up in one direction and concave down in another is what makes it neither a minimum nor a maximum. Here's the statement of the second derivative test. Theorem. Suppose x0, y0 is a critical point of the function f for which the derivatives are equal to 0. Let d be the quantity defined by this equation. Then there are 4 cases to consider. If d is positive and the second partial derivative with respect to x is negative, then f has a local maximum at x0, y0. If d is positive and the second partial derivative with respect to x is positive, then f has a local minimum at x0, y0. If d is less than 0, then f has a saddle point at x0, y0, and if d equals 0, the test yields no information. The quantity d is known as the discriminant of the function f. This quantity can be written as the determinant of a matrix, and this form gives a hint about how we may generalize this to higher dimensional functions. To review, in order to find the local extrema of a function, you first identify the critical points by finding where the first derivatives are 0. Then you use the second derivative test to attempt to classify them as minima, maxima, or saddles. And there's also the possibility that the second derivative test will give no result. In the next video, we're going to look at the case of a restricted domain. The first and second derivative tests help us to find the extreme values based on the shape of the graph. But there are times that we are working on a restricted domain where that restriction creates a minimum or a maximum. Here's an example of this from single variable calculus. Notice that at the right endpoint we see the absolute maximum value for the function on the restricted domain, but that maximum is basically a construct of restricting the domain. If we extended the domain, the function looks like it would continue upward. There is a similar effect that happens in multivariable calculus. However, we need to be a bit more thoughtful. For a single variable function, the domain is a line segment, and the boundary is just the endpoints. For a function of 2 variables, the domain is a region in the plane and the boundary is a curve, and we have to check the entire curve for extreme values. But before we do that, we will state the extreme value theorem, which also has a single variable calculus equivalent. Theorem. Let f be a continuous function on a closed and bounded region R. Then f has an absolute maximum and an absolute minimum in R. This is an example of an existence theorem. Extreme points are guaranteed to exist for functions that meet these requirements. But the theorem does not tell us how to find the absolute maximum or minimum, nor does it say that the points that attain these values are unique. All it says is that such points are guaranteed to exist. The words closed and bounded refer to certain properties of the domain. Closed means that the limit points of sequences in the domain are also in the domain, and bounded just means the domain doesn't extend infinitely. We're not going to dwell on the technical details of these terms, but you should do your best to remember them for when you take a course in topology. The book provides a 4-step process for identifying the minimum and maximum of a function on a closed and bounded region. Step 1. Find all critical points in the interior. Step 2. Find all the critical points on the boundary. Step 3. Evaluate the function at all the points from the first two steps. Step 4. The minimum and maximum are the smallest and largest values from step 3. We're going to do example 10.7.8 from the book to demonstrate all of these steps. The full details of the calculations are in the book, so we're just going to focus on the big ideas. We want to find the extreme values of the function t of xy is equal to 2x squared plus y squared minus y, bounded by the equation x squared plus y squared is less than or equal to 1. Notice that the domain is a circle of radius 1 and its interior. The first step is to find the critical points of the interior. Setting the first derivatives equal to 0, we end up with the point 0, 1/2. Since this point is in the interior of the region, we need to include it. While we could use the second derivative test, it's not necessary since we're just going to evaluate and compare the values in step 3. That's a nice feature of finding extreme values on a closed and bounded region. For step 2, we need to parameterize the circle of radius 1. We know that we can use r of t is equal to cosine t sine t for t between 0 and 2 pi. So we plug this into the function capital T to turn this into a function of a single variable. And for this we can just use our single variable calculus skills. Taking the derivative and setting it equal to 0 gives us the equation cosine of t times negative 2 sine t minus 1 is equal to 0. Solving this gives us t equals pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. You may have to review some trigonometry for this, as it goes back to the concept of using reference angles and knowing in which quadrants the sine and cosine functions are either positive or negative. Strictly speaking, we should consider the endpoints where t is equal to 0 and t is equal to 2 pi. For this situation, extending the domain just means tracing the circle periodically, so this won't create any more potential extreme values. But if this were a rectangular region, those endpoints would be important. Now we're at step 3. We're going to calculate capital T at all the points we got from the previous steps. There was 1 point from step 1 and 4 points from step 2. Remember that little t gives us a coordinate by plugging it into the parametric equations, but we can also plug it into the single variable formula that we created. The last step is to identify the smallest and largest values and declare those to be the minimum and the maximum. The smallest value is negative 1/4, which happens at 0, 1/2. The largest value is 9/4, and it appears twice at plus or minus square root of 3 over 2, negative 1/2. This is one of the first truly multi-step problems of the course. As the problems get longer, it's important to remain organized in your presentation. This will help you to think more clearly and will help others to understand you better. There is no single right way to do this, but I recommend blocking off your work into steps. For step 4, I recommend writing your conclusion as a sentence rather than just putting a box around a number and writing a single word next to it. This may seem like a small thing, but communication is central to mathematics, and the sooner you learn to work and think in complete sentences, the better. The method of Lagrange multipliers is, at least in my view, one of the great magic acts of multivariable calculus. It's a simple idea that proves itself to be extremely powerful. The underlying logic can feel a little confusing at first, and the actual computational process can sometimes be complicated, but it's such a clever and insightful way to solve the problem. What is the problem? In the previous section, we were trying to find the extreme values in a two-dimensional region. The second step was to find the critical points along the boundary of the region. For a simple region, like a rectangle or a circle, it's not hard to set up the parameterization. But if the constraint were any more complicated, it would basically be impossible to parameterize it. The method of Lagrange multipliers does this step without parameterization at all. We're going to be working with two functions. The first function is f, which is the function that we're trying to find the minimum and maximum values for. The second function is g, which is the constraint equation. We are going to assume that we can write the constraint as g of xy equals c, where c is any constant. Some books write that as g of xy is equal to 0, which makes no difference at all to the method. Let's imagine a graph of the level curves of f. Remember that these are the curves that represent a constant value of the function. To make this picture concrete, we're going to imagine this representing a mountain with the peak in the middle of the circles. Now let's think about the constraint equation. The constraint equation creates a path along the function. Every time our path cuts across a level curve of f, we must be going either up or down. For example, at this point we are climbing up the mountain, and at this point we're descending down. Somewhere in between going up and going down, there must be a point where we level out. and that point happens where our path is tangent to the level curve. It is at that point where we are no longer cutting across level curves, but instead are traveling along one of them. And that's our first observation. The critical points along the constraint happen where the constraint is tangent to the level curves. Recall that the gradient of f is a vector that points perpendicular to the level curves of f. Let's focus on the gradient at the point of tangency. That vector is going to be perpendicular to the level curve, which means that it's also perpendicular to the constraint curve. We want to find another representation of the direction that's perpendicular to the constraint curve at that point. And the trick is that the equation g of xy is equal to c is the equation of level curve of the function g. And so the gradient of g gives us a direction perpendicular to the constraint curve at the point of tangency as well. And that gives us our second observation. The gradients of the two functions must be parallel to each other. We know that two vectors are parallel to each other if they are scalar multiples of each other. And so the gradient of f must be a scalar multiple of the gradient of g. And that gives us the core relationship for Lagrange multipliers. The upshot of all of this is that this very simple formula is the way that we can solve for the extreme values of the function along the constraint. To find the extreme values, solve the system of equations given by setting the gradient of f equal to a multiple of the gradient of g. This symbol is called lambda, and it's the Greek letter L. Solving this will locate points along the constraint where the directional derivative is equal to 0, which is basically the same idea as the first derivative test of single variable calculus. Now I realize that not everyone will appreciate just how cleanly these ideas come together into this formula, but I would encourage you to think through it a couple times for yourself and really try to make the connections. It brings together a number of ideas from across the last couple chapters into a nice package. But at the end of the day, for a course at this level, you just need to show that you have the ability to solve the equation. The process itself is simple. You calculate the gradients, set the components equal to each other, and solve for the variables. A good trick for this is to not divide by any variables, because that could lead to division by 0. Instead, you want to multiply and factor using substitution or elimination. I don't quite like how the book does this example, so we're going to briefly overview the steps that I would use to solve the problem. You can pause the video to read the steps line by line, but this is something you should take as an outline and work through the algebra yourself. The function f that we're trying to optimize is x squared y, and the constraint is the equation 4x plus y equals 108. Notice that the function g is the left side of the constraint equation. When we plug this into the Lagrange multiplier equation and set the components equal to each other, we get 2xy equals 4 lambda and x squared equals lambda. Don't forget that we also have the constraint equation 4x plus y equals 108. There are 3 equations and 3 variables, and so we can begin to solve this. If we directly substitute for lambda in the first equation using the second equation, we get 2xy is equal to 4x squared. Moving everything to one side and using the fact that x is positive, we see that y is equal to 2x. We can then plug this into the constraint equation, which gives us x equals 18 and y equals 36. This is the only critical point under the conditions that x and y are positive. If we took away that restriction, then x equals 0 becomes another critical point. But for this problem, having found the critical point, we simply plug it into f to get the extreme value. And that's the basic flow for how we solve these problems. In some cases, you may have multiple critical points, in which case you just plug them all in and identify the largest and smallest values. Notice that the final conclusion was written as a complete sentence. I really want to encourage you to get into that habit. The formula for Lagrange multipliers works for any number of dimensions. Activity 10.8.3 gives you an opportunity to do such a problem. You are strongly encouraged to work through that one because experience is really the best way to learn this technique. In single variable calculus, we were able to think of integration as area under a curve. Our goal with this chapter is to increase the number of dimensions and think of integration as volume under a surface. But before we can do that, we need to do a review of the ideas we used in single variable calculus. Suppose we have a function y equals f of x, and that we are interested in the area under the curve between x equals a and x equals b. The way we did this was by approximating the area with rectangles. We're going to start from scratch and build out all the pieces of this construction. Let's suppose that we're going to use n rectangles, and we're going to make them all the same width for simplicity. To do this, we divided the interval from a to b into n pieces so that each piece has width delta x, which is equal to b minus a over n. This collection of points along the x-axis is called a partition of the interval from a to b. We can then use these points to construct vertical lines that form the heights of the approximating rectangles. But what is the height that we're going to use? We have many choices. We can pick the height to be the value of the function at the right endpoints. We can pick the height of the function to be the value at the left endpoints. We can pick the height to be the value at the midpoint. Or we can even pick arbitrary points for each interval. Each choice gives us a different collection of rectangles to approximate the area. We will generically call these points x sub I star, where I counts the rectangles from left to right. Regardless of how we choose these points, we can write down the approximate area under the curve by adding up all the rectangles. Each rectangle has width delta x and height f of x sub I star. And then we add these together to get a result known as a Riemann sum. To get from the Riemann sum to the integral, we take the limit as n goes to infinity. We're going to repeat this process, except with an extra dimension. We're going to imagine the function z equals f of xy that sits above the xy plane, and we're interested in the volume of the surface that sits above a rectangle. The rectangle is the generalization of the interval. Let's focus on the rectangle first. In the x direction, the rectangle goes from a to b, and in the y direction, it goes from c to d. In order for us to make a partition, we need to decide on the number of pieces we want to make in both directions. We'll use m in the x direction and n for the y direction. This makes a total of m times n subrectangles. This also means that the length in the x direction is delta x equals b minus a over m, and the length in the y direction is delta y equals d minus c over n. We can also see that the area of each rectangle is delta a, which is equal to delta x times delta y. Above each of these subrectangles there's a surface. If we extend this up into 3 dimensions, we get a box. The height of the box depends on the point in the region you want to use. Some common choices are the corners and the midpoint. Whatever point is chosen, we will denote it as x sub ij star, y sub ij star. The ij pair gives us the location of the specific rectangle. Once we've picked these points, we can then calculate the volume of the boxes and add them up. This gives us a double sum called a double Riemann sum. This is what we use to approximate the volume under the surface. From here, if you're given a specific function and a specific rectangle, you can actually plug in values to get a numeric result. Activity 11.1.2 walks you through that, so I'll leave that one there. The book formalizes this process into a definition. It's a bit long and wordy, so I'm not going to read it off word for word, but here's the summary. Let f be a continuous function on a rectangle R. To get the double Riemann sum of f over R, you partition the rectangle into m pieces in the x direction and n pieces in the y direction to get m times n subrectangles. Inside of each rectangle, you pick a point that will be used to calculate the height of the box corresponding to that rectangle. Then you calculate the volumes and add them together, and that result is the double Riemann sum. Just as with single variable calculus, as the number of pieces in the partitions increases, your approximation gets better and better. The double integral is the limit of the Riemann sums as m and n go to infinity. And that's formalized in the next definition. Definition: let R be a rectangular region in the xy plane, and f a continuous function over R. With terms defined as in the double Riemann sum, the double integral of f over R is the limit of the Riemann sums as both m and n go to infinity. There's a bit of a notational hiccup here. I will always explicitly write the double integral sign for a double integral. However, some people will use a single integral sign and implicitly use the dA term and the region of integration to indicate that it's a double integral. I think that's a confusing way to do things, but some of the online homework problems in the book might do that. Hopefully you'll be able to understand based on the context. Looking back at single variable calculus, one of the first issues we ran into with area under a curve is the fact that sometimes the function is negative. You might recall that we treat those areas as being negative values, so that we're actually talking about a signed area. The same thing extends to volumes. If the function goes negative, then we treat the volumes as being negative, which gives us a signed volume. So the double integral can tell us the signed volume of a region. The idea of area under a curve also leads us to the average value of a function. The concept is easiest to visualize in single variable calculus. After we've calculated the area under the curve, we can imagine redistributing the area across the whole interval and converting that area into a rectangle. The height of this rectangle is what we call the average value of the function, and we can write down the formula for it using an integral. The same thing works for double integrals, except that it's now a volume that we're averaging out into a box, instead of an area that we're averaging out into a rectangle. But it's really the exact same idea. Notice that the length of the interval has been replaced by the area of the region of integration. This is the natural generalization of the size of the underlying domain when we move from one dimension to two dimensions. There are a couple properties of double integrals that mirror the properties of single integrals. The integral of a sum is the sum of the integrals. We can also factor out constants from an integral. An integration respects inequalities, and by that we mean that if f is larger than g, then the integral of f will be larger than the integral of g. This section is mostly a review of the concepts that go into integration. On the one hand, it's new because it's a multivariable function. On the other hand, these ideas are the same ideas as in single variable calculus. In the next section, we're going to see how we can apply our previous integration knowledge to the double integrals we just created. To iterate something means to repeat a process. An iterated integral is an integral of integrals. The idea is initially intimidating, but once you understand the picture, you'll see it's not so bad. Imagine that we have some function f sitting above a rectangle. We saw in the previous section that the double integral of f over the rectangle is the volume beneath the function. Our goal is to figure out how to use our integration knowledge to calculate the volume. Following the traditions of calculus, we want to imagine how we might cut this task up into little pieces and then add them all together. We're going to start by making thin slices parallel to the YZ plane. Notice that this is like a trace because this is a region where x is basically constant, except it has just a little bit of thickness. We'll call that thickness dx. Then the volume of that slice is going to be the area under the curve multiplied by dx. And to find the area under the curve, we can use our single variable integration techniques. Notice that the lower endpoint is c and the upper endpoint is d, so that we can express the area as an integral. This is a dy integral, which implies that x is some fixed value. This formula gives us the area of the cross-section, and then we get the volume of the thin slice by multiplying it by dx. To get the total volume, we need to add up all these individual volumes. From here, we just make a substitution. We usually drop the parentheses and use position to tell us which limits correspond to the integration. You can always put the parentheses back in if you get confused, or you can also explicitly include the variable of integration in the limit. The language can be a bit confusing. A double integral is the conceptual object we created when we took a double Riemann sum and took the limit as the partition got smaller and smaller. An iterated integral is the specific process of calculating a double integral by first integrating with respect to one variable, then the other. It is an integral of integrals. This distinction is subtle and is not something that will likely cause problems, but it's worth keeping in mind. We can do this process again, but make the slices parallel to the xz plane. It turns out that the result is very similar. Intuitively, we would think that the answer we get should be the same since it's the same total volume. And while it's not true in general, it's true for continuous functions. And this result is known as Fubini's theorem. Theorem: if f is a continuous function on a rectangle R, then the double integral can be calculated as an iterated integral in either order, and the result of both calculations will be the same. When calculating these integrals, the biggest point of struggle for students is keeping track of the variables. When you're integrating with respect to x, all the y variables are treated as constants. And when you're integrating with respect to y, all the x variables are treated as constants. And when you plug in the limits, make sure you plug into the correct variable. It takes time and practice to really get comfortable with this, but it's not because it's hard. You just need the practice of mental organization and keeping the information straight. In the previous sections, we only used a rectangular domain, but what if we wanted to have a domain of a different shape? A quick answer to this is that we can always embed a finite region inside of a rectangle, and then we just define a new function that matches the given function on the initial region and 0 everywhere else. And while this works as a theoretical answer, it doesn't help us in any practical sense. So to get to a more practical solution, we're going to consider two types of regions. Some books call these type 1 and type 2 regions, but it's not that important of a distinction. The idea is that we're looking for regions that can be completely covered by thin connected rectangles in either the vertical or the horizontal direction. This corresponds to the thin slices we made in the previous section. Our basic goal is that we want to make sure those slices make sense. This first example is a typical example that can be covered using vertical rectangles. The key features here are that there is a lower function and an upper function, and that the region is bounded by constants on the left and the right. With these bounds set, you can draw in connected vertical rectangles and cover the whole region. This also gives us the information we need to set the limits of the integral. The main principle is that your integral should always be understood as lower to upper. The inner integral is a dy integral, and the bounds for that are of the form y equals something in terms of x. For the dx integral, the lower constant is a, and the upper constant is b. We've been repeating the phrase connected rectangles. This next example shows how you can get a failure of this. On the right side of this region, there is no way to cover both tips with a single rectangle without also covering areas that are outside of the region. The only way to cover just the parts that we want with vertical rectangles would be to have two disconnected pieces at the same x position, or use more advanced techniques such as dividing the region into multiple pieces. However, if we use horizontal rectangles, we can sidestep all of this. Horizontal rectangles correspond to integrating x first. The lower curve is on the left, and the upper curve is on the right. Notice that these are functions of y, and not functions of x. And the lower and upper constants are now in the y direction. We can see that the rectangles cover the region, and this gives us the setup for the integral. Notice that the order of integrals has been swapped to dx dy. This is very important. There are some regions that can be covered by either type of rectangle, but there may be practical reasons to prefer one over the other. Consider this triangular region. It's not hard to see that this can be covered with both horizontal and vertical rectangles. However, it turns out that if we use vertical rectangles, it will be slightly more complicated. To understand why, we have to think about the functions involved in defining the boundary. The lower curve is straightforward, but the upper curve is actually two separate functions. This means that when we set up the integral, we're going to have to break it into pieces. Sometimes this is a necessary step, but in this case it can be avoided by using horizontal rectangles instead. This arrangement gives us one lower function and one upper function, and this means we can set up the integral as one piece. I strongly recommend that students graph the region to help them visualize it. There's too much going on to try to keep it all in your head. We're going to work through example 11.3.3. We're going to set up the integral using both a dx dy and a dy dx integral to give you more exposure to that process. The full calculations are in the book, so we won't spend time on that. We really just want to focus on setting up the integrals. Here's the region of integration. For the first time through, we're going to integrate with respect to y first. This tells us that we will be looking at vertical boxes and that the limits of the inner integral will be of the form y equals something. If we look at the graph, we can see that the lower function in the y direction is the line y equals 0, and the upper function is the diagonal line. By doing a quick slope-intercept calculation, we can get that the equation for the line is y equals 3/2 x. And that sets up our inner integral. For the outer integral, we simply look at the leftmost and rightmost parts of the region. The leftmost is at x equals 0, and the rightmost is at x equals 2. Now let's look at the other direction. With the x integral first, we are looking at lower and upper functions to be of the form x equals something. The upper limit is x equals 2, and the lower limit is the diagonal line again, but we need to write it in the form x equals something. In this case, it's easy to get the equation x equals 2/3 y for the lower limit. Then the y limits are y equals 0 and y equals 3. And now we can set up the integral. Sometimes the region of integration will be implied in the limits of the integral. In these situations, it's helpful to sketch the graph of the functions in the limits to help you visualize the region correctly. This is especially important if you end up swapping the order of integration. You usually will not be able to do that without having a graph of the region. There may also be times when the integral itself is harder to integrate in one order compared to the other, and you won't necessarily be able to determine this in advance, so you may simply have to set things up and see what happens. One last observation for this section. For integrals over rectangular regions, we had a formula that gave us the average of the function on the region. The same equation holds for general regions. The function a of r is the area of the region, which used to be a rectangle but now can be anything. In some cases, you may have to integrate to find the area between the curves. However, if the region is a known shape, such as a triangle, a rectangle, or a circle, you may be able to use geometry to calculate the area instead of setting it up as an integral. As much as possible, you will want to find ways to simplify your work instead of blindly following a fixed process. This section expands our capacity to work with double integrals, which will help us in the coming sections. Make sure that you do the exercises to get enough practice with these integrals, as they are only going to get more and more complicated from here. In this chapter, we're going to look at a number of applications of double integrals. I'm going to take these in a different order than the book. In the previous section, we worked on setting up double integrals over general regions by thinking about covering those regions with either vertical or horizontal rectangles. It turns out that we can take those ideas and use them to calculate the area of those regions. The key idea we want to work with is the same integration concept we've been using throughout the chapter. To calculate the total area, we want to cut it up into a bunch of little pieces and then add them all up. Here's the notation that should feel familiar. The dA term is sometimes referred to as the area element. And while this is formally a double integral, we should really think of it as an instruction that says cut up your region into a bunch of small pieces and add up their areas. The area element has multiple forms depending on the specific problem and application. Its value will depend on the shapes of the pieces you create when you cut up the region. So far, we've been working with rectangular regions based on how we set up the double Riemann sums a couple sections ago. We've been using dx times dy and dy times dx as the area element because that's from the formula for the area of a rectangle. This also means that when we're thinking about our regions, we've been cutting them up into little rectangular pieces. As the rectangles get smaller and smaller, we get better and better approximations. And as long as everything is mathematically nice, the limit converges to the correct value. It's worth noting that there are other ways to cut up a region, and if we use a different shape for the area element, then we end up with a different formula. In some cases, those alternative area elements are a better match for the region of integration, and this can lead to some computational simplifications. We will talk about this in more detail in a later section. You may remember that in single variable calculus, we were not only able to find the area below a curve, but we were also able to find the area between two curves. We want to elaborate on the connection between that formula and iterated integrals. For single variable calculus, we were calculating the area of a bunch of rectangles and summing the results. The difference term in the integrand is measuring the height of the rectangles, and the dx term corresponds to the width. When we were setting up the limits of integration for iterated integrals, we were looking at the exact same picture, tracing out that vertical strip corresponded to the dy integration. In fact, we can rederive the formula by just working out the first step of the dy dx integral for the area. It's important to make these connections because this is what forms the foundation of other applications of integration. We're now going to switch gears and look at a particular application of double integrals. A lamina is a fancy term for a flat, thin object. It should remind you of the word laminate, as in putting a thin sheet of plastic over a sheet of paper. You can think of a thin disk of plastic as an example of a lamina. Our goal is to calculate the mass of a lamina, but we are going to consider cases where the lamina may not have a constant density. And so we have to figure out how to put mathematical language to this situation. Density is a ratio of mass to some unit physical dimension. In our case, we're going to be looking at mass per unit area because we're working with a flat, two-dimensional object. But this could just as well be a linear density or a volumetric density. Let's take a small piece of lamina at the point xy and calculate both the area and the mass of that piece. We can take that information to get the density of the lamina at that point. And if we do that for the entire lamina, we would get a function that tells us the density of the lamina at every point. We can also clear the fraction to get this useful relationship. The mass of a small piece of lamina is equal to the density multiplied by the area. This formula holds for any type of density if you replace the area element with the appropriate measurement for the given situation. Now that we've worked with the concept of density, let's try to get the total mass of the lamina. The total mass m is the sum of all those small masses dm. Each small mass can be calculated as the density multiplied by the area, which we will write as dA. So this is the formula for the total mass. From here, it's just setting up the integral as before. In many problems, the density formula will simply be given to you, and you'll need to make a substitution and do the calculation. But in some problems, you will need to come up with the formula yourself. Most of those problems will give you the density using phrases such as proportional to or inversely proportional to. As a quick reminder, if A is proportional to B, then we have A is equal to KB for some constant K. And if A is inversely proportional to B, then A equals K over B for some constant K. These two basic relationships can be extended to more complex situations. It's just a framework for how we express relationships between quantities. If the density is proportional to the distance from the origin, then we would have that delta of xy equals k times the square root of x squared plus y squared. If you pay attention to the language, you should be able to make the connection between the words and the equations. In the next couple sections, we're going to look at the concept of the center of mass of a lamina and take a look at some probability theory. The applications from the previous video were primarily about setting up integrals. We're now going to see how we can use that ability to address more complex problems. The center of mass of an object can be thought of as the balance point of the object. For a circle, it should be intuitive that the balance point is right in the middle. But for a half circle, you can probably intuitively recognize that it's somewhere along the line that cuts it into 2 quarters, but where exactly along that line is not at all clear. This problem gets even more complicated when we think about objects where the density is different in different locations. In order to develop the formula for the center of mass, we will start with balancing 2 objects along a massless one-dimensional bar. The 2 objects have different masses and are located at different positions. In order to talk about these positions, we're going to introduce a coordinate system. How do we find the balance point? Let's call the balance point x bar, and we can intuitively see that it's somewhere between the masses. What causes the bar to tip? It turns out that this is related to the torque the masses create around the balance point as gravity pulls on them. If the sum of the torques is 0, then the bar will be balanced. Otherwise, it will tip over. And while we could go through this whole discussion using vectors, it's easier to note that when the force is vertical and the bar is horizontal, we can use that torque is equal to force times distance. The force is due to gravity, and the distance can be calculated since we know the positions. We'll say that the objects to the left of the pivot produce a negative torque, and the objects to the right of the pivot produce a positive torque. This corresponds to the right-hand rule. After some quick algebra, we get this equation, which gives us a strong hint for how we might generalize the situation. Let's do some quick algebra on the general form. First we distribute, and then separate the sum into 2 pieces. Notice that x bar is constant, so it can be factored out of the sum. Then we move the second sum to the right and divide by the first sum to solve for x bar. And this is the formula to get the center of mass for 1 dimension. How can we handle this in 2 dimensions? It turns out that we can view each dimension independently of each other. To find the center of mass in the x direction, we view everything from the point of view of the x-axis and reduce it back to a single variable problem. Another way of saying this is that we're creating a vertical line as a balance axis. We can do the same with the y direction. Then bringing those together gives us the full form of the equation for the center of mass. This is a good start, but we need to move from discrete masses to a continuous mass in order to determine the center of mass of a lamina. Fortunately, we've developed all the appropriate skills in the previous section, so we just need to apply them to our situation. Conceptually, we're just going to take our lamina and cut it up into a bunch of pieces, and then use our work with discrete masses. In the limit as the pieces get smaller and smaller, we change the sum to an integral. The only trick is we need to think carefully about which part is cut up into pieces. In this case, the mass is the part that is being cut up, and so the mass becomes dm. This gives us the conversion for the various sums. But then we need to use the fact that the mass is related to the area element through density, which we can then substitute in. From here, it's basically just the matching game to get the center of mass. When it comes to working out these problems, it's mostly about keeping the computational mess organized. When I work on these problems, I calculate the mass of the lamina separately rather than putting it into one gigantic fraction. I find it makes my life a whole lot easier to not have fractions made out of double integrals. There are simply too many ways for me to make mistakes. As you do these problems, you can sometimes use symmetries to help simplify your work. While you should be able to grind out long computations, the use of symmetries is a way of learning to think ahead and work more efficiently. Sometimes you can use both a geometric symmetry and an algebraic symmetry together. If both the region and the density are symmetric about an axis, then the center of mass for the opposite axis is 0. The explanation for why it's the opposite axis is a bit wordy, but the pictures make this intuitively obvious, so it's better just to focus on the picture. Another type of symmetry shows up in the integrals. If your interval of integration is symmetric about 0, and the function you're integrating is odd, then the integral will simplify to 0. You can also separate out the odd parts of the integral from the rest of the integrand, which may help you to simplify your work. The common odd functions are odd powers of x and the sine function. Just be certain to double check the limits and check that the function is odd before applying this trick, otherwise you're going to make mistakes. But if you can correctly identify when this happens, you can save yourself a lot of work. So it's worth keeping an eye out for these things. The last application comes from probability theory. Students are usually introduced to probabilities using a discrete framework. We can imagine a box that contains one red ball and 3 blue balls and compute the probabilities of the different outcomes by counting the number of balls of each color and dividing by the total number of balls. But there's also a geometric framework for probabilities. Imagine we have a spinner that's broken up into colored regions as shown here. What is the probability that we would spin and end up on blue? Our intuition tells us it's the same as with the balls, but we need to do some work to set it up more carefully. When we spin the spinner, the end result is an angle that we can take to be between 0 and 2 pi, and that makes the interval from 0 to 2 pi our sample space for our possible outcomes. Each point in the sample space corresponds to either red or blue, so we can label that axis by the color. If our spinner is perfectly fair, then every single value from 0 to 2 pi would be just as likely as every other, and so we should be able to represent the probabilities with a constant line. We can then color from the theta axis up to the line to create a geometric representation of the probability. Notice that the ratio of the areas gives us the same results as before. But let's change the picture a bit. Let's pretend that the spinner is stickier in the red area than the rest of it, so there's a higher chance of it stopping there. We can represent this by increasing the height of the red area and decreasing the height of the blue area. Now the geometry shows that the chances of getting red are larger than before because the ratio of red area to blue area is greater. The second example gives us the insight we need for this section. The function that gives the height of the rectangles is known as the probability density function. Let's take a look at the definition. For a function f to be a probability density function on a set S, it needs to satisfy the following conditions. f of x is greater than or equal to 0 for all x in S. This just means that there are no negative probabilities. The integral of f of x dx over S is 1. This just means that there's a 100% chance that something in S is going to be chosen. The probability of x being between a and b is the integral of f of x dx from a to b. This is how we convert the probability density into a probability. This is analogous to integrating over a mass density to get mass. The probability density function is the function that gave the heights of the red and blue graphs that we had earlier. For any interval that we choose, the probability of the spinner stopping in the interval is the integral of the probability density function over that interval. Right now, we're looking at just one variable, but we can expand this to 2 variables and get a joint probability function. With a joint probability, we are looking for 2 events to happen at the same time. So instead of a spinner, we might think of a dartboard where the location of the dart is described by both the angle and the distance from the center. If we're working with two independent variables, then this hints at needing a double integral to calculate probabilities instead of a single integral. Here's the definition for a joint probability distribution function. f of xy is greater than or equal to 0 for all x, y, and d. The double integral of f of xy over d is 1. The probability of a point xy being chosen so that the point is in the region S is given by the double integral of f over s. You might notice that the language used here is slightly different from the language of the book. The book specifically sets up the probability density calculation as a rectangular region instead of a general region. But that difference doesn't change the core meaning of anything. Once this is set up, everything is a matter of doing the calculation and learning to interpret the meaning. Activity 11.4.5 is a good activity for introducing many of the essential concepts. A company is making smoke detectors, and they require components from two different suppliers. Each component will have a lifespan, which is some sort of probabilistic value because that's just how things work in manufacturing. The joint probability function gives the probability density for any specific combination of lifespans. The book goes on from here to walk you through how you can use this function and pick different regions of integration to get meaningful results. I'll leave that for you to work out for yourself. You may find it helpful to sketch a graph of the domains of integration when you're working through this, just to make sure you understand what's happening. Remember that every point corresponds to a pair of life expectancies, and that the joint probability function is giving you the probability density for that specific pair of life expectancies. We're going to start this section with a review of polar coordinates. You probably saw polar coordinates in your trigonometry class, but it's good to take a moment to review the basics. Polar coordinates is a coordinate system set up around circles that are centered at the origin. Locations in this coordinate system are denoted by a pair of values r theta. The r value corresponds to the distance from the origin, and theta is the angle to that point as measured from the positive x-axis. So the point 3 pi over 4 is on the circle of radius 3 at an angle pi over 4. We can relate points in polar coordinates to points in rectangular coordinates using right triangle trigonometry. If we start with a point xy in rectangular coordinates, we can use that point to draw a right triangle. We can then label the length of the legs of the triangle. This allows us to calculate r by using the Pythagorean theorem. The angle at the origin is theta, and we can set up an equation to get its value using the tangent function. Conversion in the other direction is also an exercise in right triangle trigonometry. The same diagram gives us the formula x equals r cosine theta and y equals r sine theta. It's important to note that theta is not uniquely defined, as you can increase the angle by 2 pi and end up in the same location. This allows us to continuously wrap around the origin instead of having a discontinuous jump in the angle from 2 pi all the way back down to 0. The big idea is that we want to be able to integrate using polar coordinates. This is useful because some integrals are more circular than rectangular, and so it is helpful to be able to use a more natural coordinate system. In fact, some integrals are impossible to do unless they're done in the appropriate coordinate system. The basic integral can still be set up as a double integral using the area element dA, but we can no longer use dx dy to represent that because that corresponds to rectangular coordinates. Instead, we need to use a polar rectangle, which are the shapes that we create when we draw the lines of constant r and theta. However, it's not quite as easy as just using dr d theta. The problem is that you can have the same values for dr and d theta and end up with two different areas. This is because the area also depends on how far from the origin you are. So we will need to figure out how to compensate for that. The trick is to think about the geometry of the situation. The space between the two radii creates an annulus, which is a washer-shaped region. The space between the angles is what gives us the polar rectangle. Activity 11.5.3 walks through the process of calculating that area, and then taking the limit as the r and theta values get very close to each other. The end result is that you get dA is equal to r dr d theta. And that area element gives us what we need to convert everything into polar coordinates. Here's the formula for the double integral in polar coordinates. This feels complicated, but all it's saying is that you substitute r cosine theta for x, r sine theta for y, and r dr d theta for dA. And then you need to set up your limits and integrate. Setting up the integrals can be tricky because you're probably not as familiar with polar graphs. For the d theta integral, most problems are simply going to have constants, and so that tends to be easy. For the dr integral, you're trying to trace from the lower curve to the upper curve, where the curves are functions of the form r equals something in terms of theta. In the r direction, you can think of lower to upper as inner to outer, tracing outward from the origin. You may need to sketch the polar graph to figure out which is which, but once you've done that, it's no different than in rectangular coordinates. When doing these problems, it's helpful to remember the Pythagorean identity. This will be useful when making substitutions. The most prominent example comes from the expression x squared plus y squared. In fact, in general situations, when you see the combination x squared plus y squared, that is sometimes a hint that you may want to think about using polar coordinates instead of rectangular coordinates. This gives you the basic groundwork for working with integrals in polar coordinates. As with so many other things in calculus, you're going to need to invest some time working through problems to get comfortable with it. The book has both activities and exercises to guide your practice. When we introduced parametric curves, one of the benefits we discussed was that we could trace any curve we wanted. We were no longer restricted to working with paths that were functions of the form y equals f of x. The step up to parametric surfaces is the same thing. The simplest example to think about is a sphere. If we tried to use z equals f of xy to capture the shape of a sphere, we would only be able to capture either the top half or the bottom half, but not both at the same time. We are still going to use vectors to locate points, just as we did with curves, but now we're going to have two input variables, which corresponds to the two dimensions that exist on the surface. We want to talk through the process of creating a parameterized surface. An instructive example is the torus. A torus is basically a donut-shaped region. How can we describe this shape using parametric equations? We first have to carefully define the shape. We will begin with a circle of radius a on the xz plane centered at the point b0. Then we will rotate this shape around the z-axis. We will first begin by getting parametric equations for the circle. We will use the variable t for this. This should be familiar with your previous work with parameterizing circles. We do need to make a couple changes since we are in the xz plane instead of the xy plane, and we've shifted the center away from the origin, but neither of these should be too complicated. We now need to think about how this shape is rotated around the z-axis. Rotation around the z-axis does not change the z-coordinate, so we will focus on just the x and y coordinates. Each point along the circle gives us a radius with respect to the z-axis. We'll call that radius r for now. If we want to take this point and rotate it around the z-axis, we would be tracing out a circle of radius r parallel to the xy plane at a fixed height of z. We know that the parametric formula for such a circle is r cosine s, r sine s, z, where we're using the parameter s because t has already been used earlier. The values r and z come from the first part, and so we just need to make the substitution from the original circle to get the final result. What does this vector formula mean? For every pair of values st, we get a point somewhere along the torus. And based on the construction, the s value gives us an angle when looking down the z-axis, and then the t value gives us the angle relative to the center of the tube. Activity 11.6.2 works through creating a parameterization of a sphere. This one is particularly important to work through because it lays the foundation for spherical coordinates, which we will discuss a couple sections from now. Just as we could parameterize curves based on functions, we can also parameterize surfaces based on functions. For curves of the form y equals f of x, our parameterization was t f of t. For surfaces of the form z equals f of xy, we use st f of st. The same warning applies to this as with parameterizing curves, in that you should not use the coordinate variables x and y as your parameters. Doing this creates confusion and can lead to problems down the line if you're not careful. Now that we have parameterized surfaces, we can try to do some calculus with them. Our goal will be to come up with a formula for the surface area of a parameterized surface. This derivation has a lot of steps and draws on a lot of ideas, so you may need to go through it a couple times. When we were looking at polar coordinates, we saw that we made a small polar rectangle when we made small changes to r and theta. When working with a general parameterization, we're going to get some other type of rectangle. Just as with polar rectangles, these aren't actually rectangles. They are some sort of warped shape, but we're going to refer to them as rectangles because there isn't a better word to use. You can see these rectangles on the images of the torus and the sphere from the book. Notice that towards the top of the sphere, the rectangles are getting quite warped. All of these rectangles come from drawing out curves of constant s and t. Again, we can think about polar coordinates as a model. The polar grid is nothing more than drawing curves of constant r and theta. We want to do the same thing with our general parameterization. So now we come down to the real meat of the problem. How do we calculate the area of one of these rectangles? Let's pick some ordered pair S0 T0 and imagine drawing a rectangle where we change the parameters by ds and dt. This rectangle is formed by the curves where s and t are constant, and we know that the sides can be labeled by these equations. This region can be roughly approximated by a parallelogram. The key insight is that the sides of the rectangles are curves of constant s and t, so that the tangent vectors can be used to give us their directions. But the tangent vector is only a direction and not the length of the vectors. To get the appropriate length, we can think of this using differentials. The partial derivative of r with respect to t gives us the vector tangent to the curve of constant s. It is the amount of change in position per unit change of t along the curve. So if we want to approximate the change in position moving along that rectangle, we would use partial r partial t multiplied by dt. That dt term accounts for the step size that we're taking in the t parameter. The same idea works in the s direction. And now we use the fact that the length of the cross product of two vectors gives us the area of the parallelogram spanned by those vectors to get our area element. We get ds is equal to the length of r sub s ds cross r sub t dt. Because of the properties of the cross product, we can factor out the ds and the dt, giving us this alternative representation. The book uses dA for ds dt, since ds dt acts just like dx dy would, but that notation can potentially get confusing if you're not careful, so I'm going to leave it like this. Then to get the total surface area, we integrate over all the small surface areas, and that gives us our final formula. Just as with the other section, once you have the formula, it's a matter of doing some practice calculations to get comfortable with it. All of the conceptual work is in the derivation, and the calculations are just a time to practice. Pay attention to the limits and sketch out the region of integration if you need to. At the start of this chapter, we went from a single integral to a double integral. A triple integral is next in the progression. Fortunately, the ideas themselves are not any more complicated. The only real challenge is the change of the visualization. When we had a single integral, we saw it as area under a curve. For double integrals, we saw it as volume under a surface. But for triple integrals, we don't really have any more space in our three-dimensional visualization to describe it geometrically. This forces us into a more abstract setting, where we're no longer thinking about a physical dimension, but simply as adding up the values of a function multiplied by the volume element. We'll start with the definition of a triple Riemann sum. This is a long definition, but everything functions pretty much the same way as it did with the double Riemann sum. The primary difference is that there's a third dimension floating around, so we have sub-boxes instead of sub-rectangles. In the same way as before, we would pick a point within each box and add up the function values multiplied by the volume of the individual boxes. And once we have this set up, all of the ideas from before can be pushed forward into 3 dimensions. When we take the limit as the size of the boxes go to 0, we convert this into a triple integral. The symbol dv is meant to represent a little bit of volume. Although this notation has a lot of symbols, you should be comfortable enough with the ideas that it's not too bad. We have 3 integrals because we have 3 dimensions to integrate. From here, we can look at our 2-dimensional ideas and see how they look in 3 dimensions. In 2 dimensions, we work with areas, and in 3 dimensions, we work with volumes. The average value of a function on a region is the same idea, just replacing the denominator with the appropriate quantity. Notice that this fits with the pattern of previous formulas we had. To calculate the mass of an object, we just integrate the density multiplied by the appropriate differential element. The formulas for the center of mass generalize similarly, and you can look it up in the book if you want. At this point, we have observed that these formulas mirror our previous formulas. We have not actually talked about how to set up these integrals. Fortunately, it's conceptually the same as before, following the lower to upper mentality that we've developed. The only catch is that the lower and upper surfaces are more difficult to keep track of, and you really need to pay attention to what's happening. Let's look at example 11.7.5. Here, we are asked to find the mass of the tetrahedral region of a particular density. You can get from the equation of the plane to the graph by sketching the x equals 0 and y equals 0 traces, as well as the z equals 0 level curve. We're not going to worry about the integration part itself, because it's just a bunch of calculations that are worked out in the book. We're going to focus on the ideas for setting up the integral. The most intuitive way is to do the dz integral first. What this means is that you want to think about the lower surface and the upper surface. The lower surface is the z equals 0 plane, and the upper surface is the slanted plane. The book gives us the equation for this, which we need to put into form z equals something. The challenging part is to think about what this means for the remaining two integrals. The idea is to think about lines in the z direction that fill the region. What are the xy coordinates that you will need to account for all of those lines? In this case, it's the triangular shape at the bottom of the region. But that doesn't always mean it will be that. For each problem, you will need to think about where those vertical lines will be drawn to fill the volume, and use that as your guide. Another way to think about this is to view the picture looking down from the positive z-axis and look at the shape that you see from that perspective. I've found students to be a mixed bag with this, depending on just how comfortable they are with visualizing shapes in 3 dimensions. So you're just going to have to give it a try and see what works best for you. We still need to set up the integrals for the region in the xy plane, which requires us to find the equation for this diagonal line. That line comes from the intersection of the slanted plane and the z equals 0 plane, which gives us the substitution we need. In other problems, that boundary may be the intersection of other types of surfaces, so you'll just need to think carefully to make sure you can understand what's going on. But once we've reduced it to a 2-variable problem, then the setup should feel more familiar. If we do this as a dy integral next, we will have y equals 0 as the lower curve, and y equals negative x over 2 plus 3 as the upper curve, and the x limits are 0 to 6. Putting this all together, we get this as our integral, and we would still need to work it out. Fortunately, the integration steps are straightforward. You do need to work very carefully and cleanly, as small mistakes like missing a negative sign can be extremely difficult to locate and correct. Very few students find this to be easy the first few times. The book has multiple activities to help you with this process, and you're strongly encouraged to work through all of them. It's important that you take your time and think through everything carefully so that you make sure you really do understand what you're doing. Just as the two-dimensional plane can be described using either rectangular coordinates or polar coordinates, we have multiple ways of describing three-dimensional space. In this video, we're going to focus on cylindrical coordinates, and in the next video, we'll discuss spherical coordinates. Cylindrical coordinates are what you get if you take polar coordinates and just drag it up into 3 dimensions. The core shapes that we get are cylinders, which is where the name comes from. The z-dimension is the same as the z-dimension in rectangular coordinates, and so the equations going back and forth between the two coordinate systems is basically unchanged from before. To go from rectangular coordinates to cylindrical coordinates, we use the relationships r equals the square root of x squared plus y squared, and tangent theta equals y over x, and then leave the z value unchanged. To go from cylindrical to rectangular, we use x equals r cosine theta, y equals r sine theta, and the z is unchanged. Setting up a triple integral in cylindrical coordinates requires us to get the volume element dv in terms of the variables r, theta, and z. Fortunately, we can use a general property of volumes to calculate dv. When you have a shape where the volume is created with constant cross-sections, then the volume is the area of the cross-section multiplied by the thickness. We know the cross-sectional area from polar coordinate integrals, so we multiply that by dz to get that the volume element is r dr d theta dz. This allows us to immediately write down the triple integral in cylindrical coordinates. The limits of the integral follow the same pattern as before by always working from lower to upper. The z direction is often integrated first, which then leads to creating an area in the xy plane, which can be broken down using polar coordinates. In these problems, you usually go back and forth between cylindrical and rectangular coordinates using the relationship r squared equals x squared plus y squared. It's worth taking a moment to look at a couple basic shapes described in cylindrical coordinates. All of these shapes are rotationally symmetric around the z-axis. You basically take the shape of a graph and rotate it around the z-axis to get these volumes. This makes sense because cylindrical coordinates are built around that type of rotation. The equation z equals r gives us an inverted cone that goes out at a 45-degree angle from the origin. If we let r be both positive and negative, we get a double cone. In general, lines will lead to cones. If the slope of the line changes, then that will be reflected in the shape of the cone. And shifting the y-intercept will change the location of the tip of the cone. The best strategy is to graph the line in the plane and think about what you get when you rotate it around the z-axis. Another common shape in cylindrical coordinates are paraboloids. These are equations that look something like z equals ar squared for some constant a. The constant a just adjusts how wide or narrow the paraboloid will be, and if the constant is negative, then the paraboloid will open downward. If you add or subtract a constant, you will shift the location of the vertex. These two basic examples formed the foundation of your intuition for graphs and cylindrical coordinates. Remember that these graphs are taking advantage of the fact that these are symmetric about the z-axis. Shapes that don't satisfy that property can be much more difficult to graph in this coordinate system. In the next video, we're going to look at spherical coordinates. Spherical coordinates are much more difficult to work with than cylindrical coordinates. In this case, all three variables from rectangular coordinates are interacting with each other. Here is the graph of the point x, y, z in rectangular coordinates. We want to get from this to spherical coordinates. Rho is the distance from the point to the origin. We can get this value using the distance formula. Theta is the same angle that we used in polar coordinates. To get this, we need to look at the image of the point when staring down the z-axis. Another way of saying this is that theta is the angle that we get in polar coordinates if we project the point onto the xy plane. Phi is the angle that is made with the positive z-axis when the point is connected to the origin. This is called the azimuthal angle and is somewhat analogous to lines of latitude on a globe, except that the reference is the North Pole and not the equator. From this diagram, we have the ability to calculate how to get back to rectangular coordinates from spherical coordinates. A trick that helps most students to see this is to use alternate interior angles and draw the angle phi at the point xyz. This helps to relate the sides of the triangles more naturally to the sides of the box. We can see that z is the side adjacent to the angle phi, and that the hypotenuse of the triangle in the xy plane is the side opposite the angle phi. Everything else is just right triangle trigonometry. You should really try to reconstruct this picture on your own from scratch. That is a good measure for how comfortable you are with the coordinate system, and the practice of it really helps to get these relationships to sink in. A good way to build intuition with spherical coordinates is to think about the shapes you get when you hold one or another variable to be constant. If rho is constant, you just get a sphere. This is because rho is the distance from the origin, and saying that this value is a constant is exactly the definition of a sphere. If you hold theta constant, you get a vertical half-plane coming out from the z-axis. It's important that you only get a half-plane and not a full plane. This is related to phi only being measured from the positive z-axis and not all the way around. Lastly, if you take phi to be a constant, you get a cone. As phi gets larger, the cone opens more widely. When phi equals pi over 2, you actually just get the xy plane. And then larger values of phi give you a cone in the negative z direction. You should try to visualize what curves you get when you hold two of the variables to be constant. If you can do that, then you should have a good understanding of how the spherical coordinate system works. Activity 11.8.6 walks you through the derivation of the volume element in spherical coordinates. We're going to leave it as an activity instead of working through it because it's a good culminating challenge as we approach the end of the book. The basic idea is that we're approximating the volume with a box, and you need to think about the lengths of the three dimensions. Everything else is just figuring out how to approximate those values. The end result is that dv is equal to rho squared sine phi d rho d theta d phi. Even if you don't fully understand the derivation of the volume element, once you have it, you should know what you need to do with it. We can just make the substitutions from rectangular to spherical coordinates and plug in the volume element to get the triple integral for spherical coordinates. The formula looks long, but that's because it explicitly contains all of the substitutions. The good news is that setting up the integral is exactly the same as before. You are looking at trying to set up a sequence of lower to upper regions that map out the final shape. The diagrams we created earlier can be extended to help think about lower to upper shapes. For rho, you get a spherical shell. For theta, you get a wedge-shaped region, sort of like a slice of a tall circular cake. And for phi, you get a conical shell, somewhat like an ice cream cone. This is probably the most difficult visualization sections for the book. You don't have a lot of experience to help you see these shapes, and so it's going to be tough. When trying to think through the regions, it's okay to sketch multiple pictures to try to get it right. You shouldn't imagine that you'll draw it right the first time all the time. But as you keep working through the problems, you should start to get a little bit more comfortable with this. Just take your time with these problems, and you should be able to make it through. It turns out that integration in polar, cylindrical, and spherical coordinates is a subset of a larger class of integration techniques known as change of variables, or change of coordinates. A change of variables is conceptually no different from a U substitution from single variable calculus, where we replace one symbol with another because it's more convenient for some reason. The challenge is that this is actually a very complex process. We're going to start with the two-variable change of coordinates, and we're going to use polar coordinates as our model. The framework for change of variables is that we have two coordinate systems. One of those coordinate systems is the standard xy plane. On this plane, we have a region R that has some sort of complexity to it. The idea is that in a different coordinate system, we can find a region S that is simpler and easier to work with that happens to map onto R under some transformation T. Optimistically, we can even hope that we end up with a simple rectangle after the change of coordinates. In this case, we might recognize this region as a polar rectangle, and that gives us the idea that polar coordinates might be a good choice. There's nothing telling us this other than our experience, and it can be very difficult to identify a good change of variables substitution in general. Notice that on the r theta plane, the region is represented as a true rectangle. We can explicitly write down this formula using our polar coordinate substitutions. Notice that under T, the rectangle in the r theta plane gets mapped to the polar rectangle. Each side of the r theta rectangle matches up with one of the curves in the xy plane. There's a warping of the shape that changes the area, and we're going to need to figure out how to compensate for that. For polar coordinates, we explicitly worked out that the warping factor was r, and that's related to the fact that the polar rectangle gets larger when r gets larger, even if you keep dr and dθ the same. In this case, we had to explicitly work out the geometry. The goal of the next section is to work that out for a general transformation. For polar coordinates, we had to use the details of the transformation and geometric considerations in order to get the appropriate scaling factor. The general change of coordinates process is a bit more complicated because we have to work in the abstract. We're going to start with a transformation that maps from the st plane to the xy plane. We will assume that the coordinates in the xy plane are denoted by the functions x of st and y of st. Now we're going to imagine tracing a small rectangle in the st plane and take a look at what happens to it in the xy plane. We'll set the bottom left corner of the st rectangle to be the point AB and the sides of the box to be delta s and delta t. When we map this to the xy plane, the three corners get mapped to these 3 points. We can see that the shape of the region is probably not all straight sides, but because the values are small, it will be close. To approximate the area, we're going to use the parallelogram formed by 2 of the sides. We can get the expressions for these vectors by subtraction. Notice that we can factor out a delta s or delta t to make these look like difference quotients. Then we can take the limit as delta s and delta t go to 0 to get these partial derivatives and differential terms. At this point, I'm diverging from the book's presentation, but we'll see that we end up in the same place when we're done. The notation is a little bit sloppy, but I think it's much easier to understand. The partial derivative of a vector function with respect to s or t is just the vector formed by the partial derivatives of the components. So these two expressions really do make sense as vectors, and we'll see what they look like in a moment. The point right now is that we can calculate the area element dA from these by taking the length of their cross product. This gives us a concise expression for the area element that we could substitute in to calculate the integral. We are now going to see that this relates back to the book's version by writing everything out explicitly. When we said that the area of the parallelogram was the cross product, we implicitly went up to 3 dimensions, but where the z-coordinate was always 0. So as we work this out, we're going to explicitly write in that dimension to make the calculations work. We will first work out the partial derivatives, and then compute the cross product. It will turn out that the I and j components will be 0, so that taking the length of the result is straightforward. This last form is the same form that's in the book. The quantity involving the partial derivatives is known as the Jacobian, and is denoted with this shorthand notation. This is actually just the determinant of this 2x2 matrix, where the pattern is that the rows all have the same dependent variable, and the columns have the same independent variable. This gives us another way to write down the area element. And now that we have the area element, we can write down the formula for the change of coordinate calculation. To do a calculation of this type, you're often going to have to come up with a substitution yourself. The problems usually give you a big hint by looking at the form of the integrand or the boundary. Usually they will imply substitutions by how terms are grouped together. For example, in activity 11.9.4, you are trying to calculate this integral. Notice how the integrand strongly suggests a substitution for x plus y and x minus y. If the problems did not point you in the right direction, you likely would not be able to do the calculation. This idea can be generalized to more variables by using a higher dimensional Jacobian. The general process is still the same, but now you have the determinant of a 3x3 matrix as your scaling factor. This is what the Jacobian looks like. We're not going to show the derivation of this because it's just too much at this stage. But if you followed along with the derivation from the previous section, you can probably come to a good understanding of how this works. For this class, you are merely expected to be able to follow the process. For example, you can verify our formulas for dv in both cylindrical and spherical coordinates by using the substitutions we developed in the previous section and just working out the details. Doing problems is a bit of a process as there are a bunch of steps, including making sure that you've got the right transformed region. But I think the book does a pretty good job of holding your hand through it. Because while the calculations themselves are not any more difficult than the problems in previous sections, the entire setup can be a bit rough. There's a reason that this is the last section of the book. But if you've been doing the exercises over the last 3 chapters, there's nothing here that you shouldn't be able to do. And that's it for this course. I hope you've enjoyed the videos and you've learned a few things about multivariable calculus. Thanks for watching.